Depending upon your geographical location, good morning, good afternoon, good evening, respected guest, senior and young participating scientists joining virtually from different parts of the world, ladies and gentlemen. It's a matter of great privilege for us to extend you all a warm and cordial welcome to the 18th 3-day International Online Conference on Mathematical Sciences for Advancement of Science and Technology. In short, we call this as MAST 2024, organized by the Institute for Mathematics, Bioinformatics, Information Technology, and Computer Science, having branches in Sweden and Japan. In short, we call this institute as IMBIC. It is a great shock to all of us that our founder president and the pillar of IMBIC, Professor Dr. M.R. Odhikari, left for heavenly abode on 29th June 2021. It is an immeasurable loss for us. He was academically active till his final days. Professor Odhikari shall remain in the heart of all the people he touched owing to his ever supportive, encouraging, and loving nature. Being the secretary of IMBIC, I would like to say a few words about IMBIC. The Institute IMBIC, a baby compared to the rich history of Kolkata, was founded in 2006 for the promotion and extension of mathematical knowledge, for the advancement of science, technology, and culture under the leadership of Professor Dr. M.R. Odhikari of Calcutta University, India, Professor Dr. Eric Trell, Linköping University, Sweden, Professor Dr. Y. Shikata, Nagoya University, Japan, myself, and 10 founder members. Professor Odhikari had a dream to found an international institute where scientists and researchers would get a platform to discuss modern sciences heavily dependent on one another for further development. So he felt an urgent need to organize an interdisciplinary scientific conference. His tireless and sincere effort to arrange and organize every year a 3-day international conference will inspire generation after generation. His never ending aspiration led the Institute to a vibrant one in India and abroad for studies and research in different areas of mathematics and mathematical sciences. Publications of high quality scientific and research level materials in interdisciplinary fields is one of the major goals of IMBIC. Towards achieving this goal, every year, IMBIC publishes a high quality proceedings. The book, Basic Modern Algebra with Applications by Professor M.R. Odhikari and Professor Abhishek Odhikari, was communicated through IMBIC and has been published in the year 2014 by Springer. The book, Basic Algebraic Topology and its Application by Professor M.R. Odhikari, was also communicated through IMBIC and has been published in the year 2016 again by Springer. Edited Springer research monograph entitled Mathematical and Statistical Applications to Life Sciences and Engineering, edited by Professor Abhishek Odhikari, Professor M.R. Odhikari, and Professor Y.P. Chobe, was communicated through again by IMBIC, and it was the commemoration volume of IMBIC published in 2017 on occasion of its 10th foundation anniversary. IMBIC Monograph 2013 edited volume entitled Contemporary Topics in Mathematics and Statistics with Applications, containing 13 articles with authors from America, Canada, Japan, Germany, Switzerland, India, and some other countries, was published in 2013 as the commemoration volume of IMBIC on occasion of 5th foundation anniversary, published by Asian Books Private Limited, New Delhi, India. Basic Topology 1 and Topology 2, authored by Professor Abhishek Adhikari and Professor M.R. Adhikari, was also published by Springer in 2022. Basic Algebraic Topology, authored by Professor M.R. Adhikari and published by Springer in 2023, were also communicated through IMBIC. We are pleased to announce the publication of a commemoration volume, which is a fitting tribute to Professor Adhikari's memory. The Corpus Index volume titled Quantitative Frontiers Exploring Applications of Mathematics and Statistics to be published by Springer in 2025. Organization of an international conference annually is a key activity of IMBIC. The primary objective of this conference is to highlight specified topics in mathematics, statistics, computer science, bioinformatics, and related interdisciplinary fields. This year, IMBIC received 171 research papers, abstracts, authored by scientists from different parts of the world for consideration of publication and presentation is March 2024 in response to the announcement on the website of IMBIC. The authors are distributed over 4 different continents, namely Asia, Europe, North America, and Africa. From India, we have received papers from 20 different states. After a careful review, only 13 scientific full papers have been accepted for publications in the proceedings of IMBIC. For the coming 3 days, we're going to witness esteemed invited speakers from foreign institutes and on different topics. So you can see that all the distinguished esteemed speakers present here, they are going to deliver their talks during the whole session. In addition to the exciting program, we are also thrilled to include a 3-day online workshop on data science, Accelerate Your Career. This workshop will provide valuable insights into the latest data science techniques and tools, helping our students build networks with industry experts and potential open doors to new career opportunities. The Institute express sincere thanks to all invited speakers, participants, members of international and national committees, all the reviewers and authors of all papers, including both which were accepted and those which are unfortunately not accepted for publication. I am sure that this scientific conference and the workshop will surely be fruitful to all of us. With that, thank you all. So this is the image from our last conference, which we made in a physical mode, and we are hopeful that in near future, we'll again have the physical mode where all of us will join together. And also, of course, we'll have the hybrid mode as well. With that hope, I end my talk. Thank you very much. So now, may I now request our next speaker for this inaugural address, Professor Erik Trell from Sweden, who is the Vice President of IMBIC. So may I now request Erik to please deliver your inaugural address.
Thank you very much, Abhishek. And it's a renewed experience every year and finding IMBIC to flower and expand. And this year's program really is impressive in terms of the number of young researchers that add novel insights and methods over a fantastic variety of themes. And I represent biomedicine primarily, being a doctor, but in IMBIC I have had the privilege to learn mathematics and even apply some of this knowledge, which I'm going to present now. I'm going to have the theme backwards to the future, going back to the future. And the first is, of course, to come back to the memory of Professor Mahim Adhikari, who has been such an important friend and mentor for this. I remember meeting him first at Imperial College in London in a discussion about physical interpretation of relativity theory, which of course was very wide from my experience. But we found each other instantly, and he learned me a lot about these things and told me not to be afraid of letting my ideas, if I had any, be exposed. And he invited me also to India because he was then president of Calcutta Mathematical Society, and I visited regularly the meetings there. Every time I felt like part of the college. And when Professor Mahim then retired, we decided that we should try and start a philanthropic, idealistic, and non-profit association for furthering knowledge among the new student generations. And we had an inauguration meeting and formed IMBIC. It has been surprisingly, you could say, constant and durable and sustained, and has developed steadily during the years. But of course, Mahim's death was a great blow, and it didn't really then affect IMBIC other than as a contained stimulus. And now Adhikari has run this company for a couple of years, and this trust has increased steadily after then. But the other aspect, going back to the future, is also a more serious one in the state of the world today. We see things develop very unfortunately, and we need to go back to many things. And this is my hope for the future, that we can come back to some kind of order where science again is coming back to the traditional forms of respect and also seriousness. And then my hope for that raises every time I come to IMBIC. And this year, for instance, I see that we have more than 100 contributions from young researchers. And I open just a page here and read what is it all about. Well, it is about future, predictive acute toxicity of dimethyl phthalate on fish, and thermal effect on hybrid nanoliquids during spin coating process, analysis of aware and unaware populations of HIV/AIDS dynamics modeling. We have propagation of love waves through an irregular surface, and we have mathematical analysis of fingers in, just the page. And it's full of the most intriguing and fascinating new topics with a range over all society, technology, sociology, medicine, and applied and pure mathematics. So I'm very enriched and hopeful by that. And my memories again go back to Professor Mahim, who I think would be very happy to see how IMBIC now really makes the way in the modern world and future. And I think I stay there for the moment and thank you for my coming back here. Thank you.
Thank you very much, Professor Eric Trell, for your nice words towards Professor M.R. Odhikari as well as towards IMBIC. It's really very hard to run without him, but still we are somehow managing with all of your support and blessings. So next, may I now request our address of guest of honor, Carl Soup, Soup's Ink Color Research from US. So Carl, could you please start?
Okay. Can you hear me okay?
Yeah, it's perfect. Yeah.
Okay. I would like to welcome everyone and thank you for being here with us. I also thank the IMBIC family for the invitation to present a paper at MAST 2024. The program committee, the organizing committee, Professor Dr. Abhishek Adhikari and his family and his students, Dr. Trell and his family. Without your support, this math conference would not be possible. This is a quote from the IMBIC webpage. The main objective of this conference is to bring specialized topics in mathematics, statistics, computer science, bioinformatics, and closely related interdisciplinary areas to the forefront. The conference will contribute to the development of mathematical sciences and their applications and bring together mathematicians, statisticians, computer and bioinformatics scientists, interdisciplinary researchers, engineers, and educators from around the world. My area of research is color, as it exists as radiation. Initially, my wild and impossible objective was to define color in terms of numbers and geometry. People were always telling me that defining color was impossible. I have never received negative comments for or about my research at the MAST conferences. I have received helpful critiques or challenging questions during presentations, but MAST is an international conference. That means that International Math Conference is world class. Yes, I've defined color in terms of numbers and geometry, which means that the things that people had told me that were impossible didn't hold me back. And at IMBIC, that there's always that encouragement and that guidance that you can receive at MBIC. And it's led me to, like, now my wild and impossible dream, which drives my research, is to try to figure out teleportation and magnetic levitation. Uh, I asked a good friend of mine for some advice, and I wanted to know what he thought I could or should do with my research. My friend, advisor, was the late Dr. M.R. Adhikari, and his advice was that I should find a way to share my research with the rest of the world. I was thinking, wow, no pressure. Professor M.R. Adhikari is one of the founders of MBIC and the yearly math conference. I am doing the research that I am doing because of his encouragement I received from Professor M.R. Adhikari. He always made me feel comfortable and a little special, and he was that way with everyone. He was just being himself and doing what he loved. And to me, that was priceless. I continue to write papers, and I'm sharing my research with the rest of the world via the proceedings of the Math Conference. And I'd like to add my thanks to the Math Conference uh, because in doing so, I found my research voice. And you can't imagine how important that is to me, because being able to do the research, put the papers together, and have a place in which I can share my ideas, again, that's something else that's just priceless. And so my appreciation for MBIC in the math conferences is just off the charts for me. So welcome to the 2024 International Math Conference, and hope you enjoy yourselves. Thank you.
Thank you, Carl, for your nice words and the activities of IMBIC and a bit motivation that you received from Professor M.R. Adhikari. So may I now request Professor Ashish Sengupta, is he here? I think he told that he might be, but he is now in another conference, so may not be here. Yeah, so now we just directly jumped into maybe Dr. Umesh Srivastava, would you like to speak a few words? You are muted. Could you please unmute yourself? We cannot hear you.
No, at present, I am not in a position to speak something.
Okay. Okay.
Yeah, in session, I will say something.
Okay. Okay. So now we just directly jumped into our vote of thanks portion. May I now request Mrs. Minoti Odhikari, the treasurer of IMBIC, to give the vote of thanks.
Good morning, good afternoon, and good evening to all of you participating from all over India and abroad in the 18th 3-day International Online Conference MUST 2024, organized by Institute of Mathematics, Bioinformatics, Information Technology, and Computer Science, in short, IMBIC. First, I shall pay homages to Professor Dr. Mohim Ranjan Adhikari, an eminent mathematician and founder president of IMBIC, who had a dream to set up Such a versatile research institute where scientists and researchers in different areas of mathematics and mathematical sciences can discuss modern sciences heavily depend on one another for further development. He had given all his efforts and energy to get it strong and stable. But when all was running smoothly, he left us suddenly on June 29, 2021, leaving a deep wound behind, never to be healing up. However, he will be remembered and living forever in his works and creations. May he rest in peace. Now, before closing the inaugural session of MAST 2024, I, on behalf of IMBIC, have had the great opportunity to propose vote of thanks to the chairman of inaugural session, Professor Dr. Abhishek Adhikari, head of the Department of Presidency University, Kolkata, India, and founder secretary of IMBIC, for giving a motivational speech on the importance of interdisciplinary scientific research work and the role of IMBIC for promotion and extension of mathematical knowledges in different areas. I convey my thanks to Professor Dr. Eric Trell, Emeritus Professor of Linköping University and the founder Vice President of IMBIC and Director of IMBIC Sweden chapter. He is a young man of 80. His enthusiastic and energetic inaugural speech is not only inspiring but enlightens and instigates the young scientists and researchers. I sincerely express my thanks to Carl Soups from Soups Inc., USA, for giving his wise thoughts and ideas in his inaugural talk. His vibrant thoughts and ideas ignite the future generations. I'm mostly thankful to Dr. Lena Trell from Sweden. She has been sincerely attached with IMBIC right from its birth. Despite her ill health, she is attending the conference on behalf of IMBIC family. I wish her a speedy recovery. I convey my thanks to the dignitaries and the scholarly participants for their online participation. I would like to thank especially to the group of young and enthusiastic volunteers, Dr. Ongshuman Das, Dr. Prakash De, Chandan Goswami, Himadri Shekhar Roy, Dr. Sandip Mondol, Suchandan Ghosh, Niloy Das, Master Oviptiyo Adhikari, whose enormous efforts and unique coordination will help the three-day international conference MAST 2024 to reach to its ultimate goal. Thank you all.
Thank you, Mrs. Odhikari, for giving this vote of thanks. So that would be the end of this short inaugural session. Now we'll move forward to our next first technical session. That would be on the, as we all know, that's a data science workshop. So that would be a part of this data science workshop, and we are already among us the two speakers, Dr. Saurabh Bhaduri as well as Shankar Narayan Mishra. So before we go into this next session, may I just request them if everything goes well. So are you ready, both of you? So we are still having 15 minutes of time. So before that, we can make our things ready.
Yes, we are ready.
Yes, sir.
We can start.
Okay, but I think since many people may join on time,
Okay.
so it's 5:45. It was scheduled, so we had some time, but we are actually, I mean, this properly punctual. That's why everything is going on time. Okay, so yeah, so if so, Dr. Bhaduri will talk first, right?
Yes.
Yeah. Okay. And let's see. So I can see that currently in our YouTube, around 62 participants are watching live, and 54 are on our this Meet link. So I haven't distributed this Meet link to many of the people, so that last time we had a problem that it was difficult for the speakers to get in. So that's why we restricted ourselves, since we have only 100 quota for that. But few of the students will certainly join. I have given to them, but through online YouTube mode, many of them, they are going to join us. So let's see. So maybe we can just start a bit, maybe at a very slow mode. Then, I mean, instead of waiting for. So what is your opinion? Whatever you feel. I think you are muted. I cannot hear you.
Actually, if it's okay, then we can start.
Yeah, we can start, because it would be on the YouTube. So if someone wants
Okay.
to, then they can just see it. Yeah.
So I will share my screen.
Yeah, but before that, it's my great pleasure to introduce Dr. Bhaduri. So Dr. Bhaduri is an assistant professor at IAI TCG Crest. He is the recipient of prestigious Rama Lingoswamy Fellowship Award by the Department of Biotechnology, Government of India in 2022 and 23, as well as the British and Irish ISMRM Chapter Mansfield Research Innovation Award in 2022. Prior to joining to TCG Crest, Dr. Bhaduri held academic positions in Symbiosis International University, the University of Liverpool, UK, the Ghent University, Belgium. He earned his PhD from Ghent University, Belgium, and his MSc from University of Stuttgart, Germany. So without any further ado, it's my great pleasure to welcome Dr. Bhaduri. Now, Dr. Bhaduri, the screen is yours.
Thank you, Professor Odhikari, for the introduction. And it's an honor to be here at MAST 2024 and for inviting me to speak in this session. So I will share my screen. Is my screen visible to all?
Yeah, it's visible and audible as well.
Okay, so yes, so the title of this talk is Introduction to Computer Vision and Image Processing. Before that, I would like to briefly talk about my research area and how it is related to computer vision and image processing. So my research focus is on neuroimaging, particularly using MRI and multimodal imaging along with artificial intelligence, particularly in the context of tumor diagnosis and treatment planning and also response to different therapies. So my work is about using multimodal imaging techniques and alongside deep learning techniques for automated segmentation of the tumor and also predicting how the treatment works. So this conference is about exploring cutting edge techniques for data analysis and interpretation. And my work aligns with this actually by integrating radiology with artificial intelligence to address real world challenges. And computer vision is the foundation of modern medical image analysis. So like I said that I use multimodal images, mainly MRI, CT, and other modalities, and combine that with artificial intelligence to detect disease progression and also to detect the type of the disease. I also wanted to talk about briefly about drug discovery. So that is also part of my research work. So drug discovery takes place as a multi-stage process where it starts from in vitro level to preclinical level, and then it goes to clinical trials. And by the time a drug goes to clinical trial, millions of dollars money are spent. And also, by the time it reaches the clinical trial, only few make it to the market. Only few are commercialized. And we need very sophisticated methods, especially imaging methods and artificial intelligence, along with computer vision, to actually assess how the drug is working. So a very good application of computer vision is if we treat the tumor using a drug, then how the treatment is working if we can track that. And that can tell us about the disease progression. And then we can actually, from these images, we can extract meaningful clinically relevant features, which we can train using machine learning models and can predict the type of the disease and also whether the disease is progressing or not. So to talk about the workflow, like how I combine radiology with computer vision. So the first step is to acquire the image using multimodal imaging methods. So that's part of the radiology. And then comes the computer vision, which involves pre-processing of the imaging data. So pre-processing means reducing the noise, normalizing the data. So that actually helps us to standardize the data. So how we reduce the noise? We apply image filters to reduce the noise. And also we can do histogram equalization and other methods to actually standardize the data to make it ready for further analysis. So the further analysis involves computer vision tasks like segmentation, where we segment out the region of anomaly from the image. And after segmentation, we extract meaningful features from the segmented area. And then we apply AI-based analysis for further classification and prognostication. So to summarize, so computer vision has intersection with machine learning and deep learning. And all of them falls under the field of artificial intelligence. Okay, so what is computer vision? So computer vision refers to the ability of a machine to see, to analyze, and to interpret visual data from the world around us. So essentially, it's about teaching a computer to process images and videos like a human does. So it kind of mimics human perception. So how it works? It actually starts by seeing. So the machine actually sees. By seeing, I mean that it captures images using a camera. And then it goes through some processing steps, or rather pre-processing steps, where we reduce the noise and other artifacts in the image so that the machine can take some intelligent decision. So by intelligent decision, it can be recognizing a face or can be detection of an object. So how a human being sees. So with the eye, you can see here that it's an image of a train station accident. So if you look at this image here, so it's a train station accident, but actually a computer sees it in terms of numbers. So it's a matrix of numerical pixel intensity values. So let's take a brief journey through the history of computer science, starting from the 1950s or the 1960s. So in 1960s, Marvin Minsky, he was a professor of MIT, and he actually gave a summer internship project to his students to develop an algorithm to automatically segment out an image into foreground and background. So to extract out non-overlapping objects from the image. And the task was very complex at that time, considering the hardware limitations and other aspects. In 1970, David Marr proposed this hierarchical vision framework, where he proposed that vision can be three types. It can be low-level vision, where it involves basic features like the edges, the textures and blobs in raw pixel data. And then comes the mid-level vision, which includes depth, surface orientation, and spatial structure. And then finally, high-level vision is about building a 3D model from these shapes. In 1990s, further advancement happened. Like Matthew Turk and Alex Pentland at MIT, they proposed the principal component analysis algorithm to kind of express facial data as a combination of eigenfaces. So this is very popular facial recognition algorithm, which came in the 1990s. And then in the 2000s, annotated data sets were used for training a model. So ImageNet was started at that time. And actually, it was a massive hierarchical data set with millions of labeled data or labeled images. And they provided high quality labeled data for supervised learning, enabling researchers to train more effective and complex models. And later on, this was actually used for the invention of AlexNet in the 2010 and the 2012, which was a very effective deep learning algorithm. I will also like to talk about this very fascinating thing about neural networks. It was like proposed by Hubel and Wiesel in 1959. So they were experimenting with the cats. And they found out that the visual cortex actually analyzes simple structures first, like the edges. And then they start processing complex patterns in the image. So how our mind works, we first try to analyze simple patterns like edges. And then we, step by step, we move to complex patterns. So before 2012, how object detection happened? So it was using hand-engineered features like the shift and the hog features, which were input to a machine learning model like the support vector machine or logistic regression. And then this machine learning model classified whether the object is a cat or a dog. And nowadays, it's deep learning. So in the 1990s, Jan LeCun came up with this LeNet, and that was very popular at that time. It used convolutional neural networks. And then in 2012, AlexNet was invented, and which was a very efficient algorithm considering the advancement in NVIDIA GPU graphics and other powerful components in a computer, and also thanks to the massive annotated data sets of ImageNet. So some applications of computer vision, where it is used. So it's used for object recognition, for fingerprint scanners, and medical imaging analysis. Some other applications include the optical character recognition, OCR, face detection, shape and motion capture, and also vision-based biometrics. So I will talk about some very interesting applications of computer vision, which we come across every day. So let's say an intelligent vending machine. So it's very popular in Japan. So if you stand in front of this vending machine, the machine detects the user's face and provides personalized recommendations about a product based on the age, the gender, or past preferences. This is also a very important application, which is the security surveillance system. So which works by detecting and tracking individuals in real time. And it plays a huge role in enhancing safety and monitoring activities and identifying threats, of course. Another fascinating application of computer vision is the optical mouse that we use almost every day. So how it works? So this optical mouse tries to recognize the surface patterns using a camera and then feeds that information to the computer to move the cursor. So this is a remarkable example of human-computer interaction, which is an application of computer vision, of course. And another interesting application is gaming using Kinect. So what happens, it tries to detect the body movement, and accordingly, it tries to enhance the gaming experience. Also, you can see here, this is an image of Doug Robel. He gave a TED talk on this, actually, so for detection of facial expression using a camera and kind of integrating that to animated characters in real time. So this is particularly useful in CGI or action movies where you have those good visual effects. So this is an example of Snapchat, which kind of recognizes the face and then tries to overlay digital elements into these real world images. So here you can see this is a face manipulation example where this guy, how he looked in his younger days and how he will look in his older days. So that can be kind of simulated using this application. So, and another important application is the autonomous navigation. So this is very popular these days. So driverless cars, which tries to which relies on computer vision to perceive the environment, detect obstacles, and make navigation decisions, ensuring safe and efficient driving. So this is an example of computer vision again for remote sensing, where the satellite images are used to monitor for environmental monitoring, for disaster management, and urban planning. So now let's dive into the basics of image processing. So first, let's understand what's an image and how the digital images are structured. So the digital images are essentially grids of tiny units called pixels, and each pixel represents an intensity value. So they can be of different types, the grayscale and the RGB images. So let's say a grayscale image, the intensity values range from 0 to 255, representing the brightness of each pixel. And then there are color images, where the image can be divided into three components, the R, G, and the B, red, green, and blue. And each have their intensities in the range 0 to 255. But when you combine them, you get the color image. Another way to represent color images is to transform them into the HSV space. So HSV stands for hue, saturation, and value. So this is particularly useful in image processing because it separates the color component from the intensity. So that can be used as a feature for training. So hue represents the type of color. So here you see the color wheel, and the color is measured as an angle between 0 to 360 degrees on a color wheel. And the saturation indicates the intensity of the color, how much pure the color is. And the value specifies the brightness of the color, ranging from black to the full intensity. So here you see the RGB image can be converted to separate components, the hue, saturation, and the brightness. Now I will be talking about the image transforms, which is very important for image processing and computer vision applications. So These mathematical tools, these image transform techniques, allows us to analyze images in alternative representations, so particularly in the frequency domain. So the first thing I will be talking about is the Fourier transform. So the Fourier transform converts spatial information, such as pixel intensities, into frequency components. So for example, here you can see this is an image of a box here. And if you do the Fourier transform of this, the center part, which is the low frequency region, contains the smooth, the low frequency information is the smooth region. And the high frequency information represents the abrupt changes like edges. And DFT is one of the methods to analyze and represent the image in terms of frequency components. So this is applied particularly in MRI, where a person goes into the MRI and the images are collected in the Fourier space, which is also called the K space. So as you can see here, the low frequency components here are the high intensity region here, and the edges are in the high frequency. So if we do a Fourier transform of this particular K space, we get back the image of the person, of the brain of the person. So, so the center here contains the low frequency information, and while the edges hold the high frequency details. Another method is the discrete cosine transform, so which is also a powerful tool to convert from spatial domain to the frequency domain. But this particular method focuses on the energy compaction principle. So you can see most of the energy is concentrated in few coefficient. So after the discrete cosine transform, most of the energy will be in few coefficients only. And we can remove some of the high frequency coefficients, and we can reconstruct the signal to exactly replicate what was what the input was. So this is particularly useful in compression techniques like JPEG. All of you know about the JPEG compression technique, and the DCT method is particularly used in JPEG compression. Another method is the wavelet transform. So the wavelet analyzes signals and images at multiple resolutions. It's very useful for identifying features at different scales. But how it's different from the DCT and the DFT, it simultaneously analyzes the frequency and the spatial components. So unlike Fourier transform, which focuses purely on frequency, the wavelet transform analyzes frequency and spatial details together, making it ideal for non-stationary data like images. So here it's an example of the image, and we can break down the image into different frequency components using wavelets. So this particular method is very useful in compression formats like the JPEG 2000. So it compresses the image into low frequency component, as can be seen here. This is the low frequency component, and then there is the horizontal detail, which contains the horizontal edges and patterns, and then there is the vertical details, which has the vertical edges and patterns, and then the diagonal details, which has all the high frequency information. So let's now discuss one of the most fundamental operations in image processing, which is convolution. So convolution is a mathematical operation that applies filters to an image. So it allows us to extract specific features like edges. It can be used to blur an image or even sharpen the image. So now let's delve into the world of image filters. So first I will be talking about image blurring, and then about image sharpening, and then edge detection. So what happens in image blurring? Image blurring is a technique for smoothing images by reducing noise and fine details. So blurring is a key pre-processing steps in many image analysis pipelines. So the primary idea of blurring is to remove the high frequency components while retaining the overall structure of the image. So this can be done by two methods, the averaging filter. So in averaging filter, you actually take the average of the neighboring pixels, which is not sometimes very much effective because it sometimes blurs the edges as well. So a Gaussian blurring method is more effective where the weights of the pixels are based on the distance from the center. So this means that the closer neighbors contribute more to the final value, preserving the image structure. So here you see an example of Gaussian blurring. Now, what is image sharpening? Image sharpening is a technique that enhances the edges and details in an image. So unlike blurring, which smooths the image, sharpening focuses on features more distinct. So like the edges and the fine details. So this can be done using a Laplacian filter, which kind of takes the double derivative of the image to detect and enhance the edges. So here you can see the nice edges in the image using a Laplacian filter. And then the edge detection, which is a very critical aspect of image processing. The main goal of edge detection is to identify boundaries in the image. And it happens by detecting areas where intensity changes significantly. So this is particularly essential in applications like object recognition, feature extraction, and medical imaging. So how we detect the edges, we take the first derivative or the image gradients. So this can be done using a Sobel filter. So this is a Sobel filter applied along the horizontal and vertical direction of the image. And you can see, you can detect the edges nicely using this. There are further methods like the canny edge detector, which can refine the edge detection using few more steps. I won't be going into details of these steps, but these two are the most popular methods for edge detection. So coming to features which are used in computer vision. So what are features? So features are crucial for image processing, and features such as edges, corners, and textures, they are essential for understanding the image's content and are used in various tasks like object detection, tracking, and classification. So one of the features is corner. So how we detect the corners? The corners are detected using, again, it's kind of similar principle to edge detection. It calculates the image gradients, and from the image gradients, it tries to calculate the corners. So there's a method called the Harris corner detection method, which is quite popular in finding out the corners in an image. So this is particularly useful for object tracking and 3D reconstruction. So next, texture feature. So texture detection focuses on identifying patterns in an image such as smoothness, roughness, repetition, or randomness. The texture detection has a wide range of applications, including medical imaging and also in remote sensing. So how we detect the features, we create a matrix called the gray level co-occurrence matrix. I won't be going into details of that, but from this gray level co-occurrence matrix, we extract some meaningful features like contrast, correlation, energy, and homogeneity. So here you can see, this is an image, and we extract the texture-based features like the contrast, correlation, energy, and homogeneity from this image. Now coming to key point detection. What is key point detection? It's a fundamental concept in computer vision. So key point detection is about identifying robust and scale invariant features in an image. So these features are crucial for object recognition and tracking tasks. So if you look at this image of Messi, you will see some points are highlighted in green, and they are kind of invariant to rotation, scaling, and other changes in lighting. And they play a big role in object detection and tracking, as mentioned earlier. So what are some key point detection methods? So this is one method, the scale invariant feature transform, or this SIFT algorithm. So using this algorithm, we can detect the key points. So here we take the concept of the difference of Gaussian. So the idea is to identify location in an image where the intensity changes significantly in all directions, such as the corners or the blobs. So these points are the key points. So in this diagram, you will see the concept of scale space representation. So an input image here can be blurred using Gaussian kernels with increasing standard deviation sigma. So this creates a series of Gaussian images like you can see here in the green. And then the difference of Gaussian is computed by subtracting adjacent Gaussian images as seen in blue. And if you calculate the extrema of these difference of Gaussian images, you will get the key points. And that can be used as features for further training. Now, from here, I will move to the convolutional neural network, which is a cornerstone of deep learning in computer vision. So CNNs are specifically designed for interpreting visual data, such as images and videos. And they mimic how human processes visual information by learning hierarchical features. So this starts by identifying simple patterns in the image like edges and corners. And this is very much useful in techniques like image classification and object recognition. So what are the components involved in CNNs? So the first key component involved in CNN is the convolutional layer. So this convolutional layer contains the filters. So for instance, here you can see it's a kernel, a filter applied to an image, and this particular kernel slides across the image to capture the feature maps. And the result of this convolutional layer can be edge detection, it can be image blurring, and other effects. Like for instance, here, if you multiply this image with this kernel, you kind of get the edges. And then comes the pooling layers. So what's the function of the pooling layers? The pooling layers reduce the spatial dimension of the feature maps, and primarily to decrease the computational load and to prevent overfitting. And some of the key components of a convolutional neural network are the activation functions. So what are the activation functions? So activation functions are the critical component in neural networks that enables them to learn and make complex decisions. So they introduce nonlinear transformation to the network, and this allows the model to learn intricate patterns and decision boundaries. So they are of many types, like the ReLU function, which is also known as the rectified linear unit. And there is a sigmoid function, and there is the tanh function. And the most popular method of these, out of them, is the ReLU function, which is the go-to choice method for modern deep learning neural networks, because it trains faster and avoids the gradient vanishing problem. So the next talk will cover some of the key features of CNN. So Shankar will be talking about the convolutional neural networks in details, and he will be demonstrating using an open data set called the BRATS data, and using a Python package to do some brain tumor segmentation. Okay, now I will talk briefly about object detection. So what is object detection? So this is a crucial area in computer vision. And let's say you have an image and you want to detect a specific object in the image. So this can be done using convolutional neural networks and using an algorithm called YOLO. You only look once. So this is particularly useful for autonomous driving and surveillance. So but how it works? So it takes an input image and divides the image into a grid, and each grid cell predicts a bounding box, the location and dimension of the object, and some confidence scores that how likely that box contains an object. And alongside, it also does some class predictions to identify what's the type of object in that particular grid. So as input, you give an image and and as output, you get all these information like the box, the bounding box of the object, what kind of object, and what's the position of the object. Okay, next, coming to segmentation, which is also an essential part of computer vision. So what it does, it breaks an image into meaningful regions by labeling each and every single pixel. So this helps us to understand the content of the image at a detailed level. So first, I will talk about the semantic segmentation. So in semantic segmentation, we label all the pixels as one as a certain category. So let's say there is a tumor in a brain image. We label the tumor as one category and the background as another category. And using this semantic segmentation, we can predict in some other images where the tumor exactly is. So this is typically done using a convolutional neural network, which is often an encoder-decoder architecture. So the encoder extracts here, the encoder extracts feature by reducing the spatial dimension, and the decoder part takes the feature and reconstructs a pixel level classification map. So this is semantic segmentation. And what is instance segmentation? It not only segments one object, but it detects multiple objects in an image and also performs the segmentation for each object. And now I will be talking about object tracking. So once you have detected an object, you also need to track the object across multiple frames. So how we do that? So this process involves advanced techniques like the Kalman filter and the deep sort algorithm, which are particularly effective in surveillance or autonomous driving and sports analytics. So first we need to detect the object. Let's say you have been given a video and you want to track a particular object. So first you need the YOLO algorithm to detect the object and to get the bounding box and the object class predictions, and then predict what the position of the object will be in the next frame using Kalman filter. Now you have to match the prediction with the actual with the actual box, and then update the track object state with the new position. And you can label using a certain ID whatever objects you are tracking. So for instance, here you can see you can track the football players uniquely. So some important learning resources which is very useful to go to the basics of computer vision and image processing. And with this, I would like to acknowledge the contribution of my lab members and also the support from funding agencies. A big thank you to all of you for listening to this talk. Thank you. Thank you very much.
So thank you very much for your insightful presentation. So I think there might be many questions. So those who are in the online mode in Google Meet, they can unmute themselves and they can ask their own questions. So any questions from or comments from the participants who are using Google Meet may come up on their own. Unmute yourself. Okay, let's see. Yeah, please carry on. Rigom, you had some questions?
Sir, it would be very nice if you like uh, tell the texture detection once more.
Okay, so the texture detection is kind of detecting the repetitive patterns in an image. So it can be done by converting the image into a matrix called the GLCM, the gray level co-occurrence matrix. So you can read about it. And from this gray level co-occurrence matrix, we can derive several parameters like the entropy, homogeneity, uniformity, energy, etc. And these are used as features when you are training a machine learning model. So you can have a look into gray level cooccurrence matrix, which can give you an idea about the texture of an image.
Thank you, sir.
Okay, there is one question on YouTube by Orgodeep Singh Aman. How the Fourier transform uses for conversion?
Okay, so Fourier transform, it's kind of representing an image in terms of sinusoidal waves, in terms of sines and cosines, and that kind of gives you the spatial location, like what kind of spatial information are embedded in the frequencies. So you can use a two-dimensional DFT or a fast Fourier transform to convert an image in the spatial domain to the Fourier domain, if I understood the question correctly.
Okay. So is it clear to Aman who asked this question? Okay, any further questions? So I cannot see any further question on YouTube itself. Okay, so one of the persons who is, yeah. So one of the participant, he wants the slide. So is it possible to share?
Sure,
the slide?
I will share the slides, yes.
Okay, great. So I think that was the question. Okay, so Rigom Bhaduri asked another question, sir, what is YOLO output?
So YOLO is a neural network, actually. It's a convolutional neural network where you feed an image as an input, and as an output, you get just a few numbers which represent the object class in terms of numbers. Like, let's say 000 means a cat, or 010 means a dog. So you will get the number as 010. And then a bounding box representing the breadth, the length, and the center position of the box. And alongside, you get the confidence score, that how much you can rely on the results. So all in terms of just a 1D vector.
Okay, so any further question? So another question from YouTube, it was saying that, sir, can you explain the gaming theory in object detection and pattern recognition?
Actually, gaming theory is not my area, actually. So I am not the best person to answer that.
Okay. So any further question from YouTube or even on Google Meet link were there? Okay, I cannot see any further questions. So, okay, if any further question, please write it on the chat box. I shall surely share with the speakers and get back to you. Okay, so if there is no further question, let's thanks once again the speaker.
Thank you.
Okay, and now we move on to our next speaker. Shankar, are you ready?
Yes, sir. Let me share my screen.
Yeah, so it's my great pleasure to introduce Shankar. Shankar Narayan Misra is a junior research fellow at IAI TCG Crest. He brings 6 years of professional experience in data science, having worked with both startups and multinational corporations. He held an MTech degree from Indian Statistical Institute, ISI Kolkata, and MSc from Indian Institute of Technology, IIT Bombay, and BSc from St. Xavier's College, Kolkata. So without any further ado, let's go for this exciting session where you might have some hands-on experience through him with real data. So, Shankar, now the screen is yours.
Sure, sir. And good evening, good morning, and good evening, everyone. Also, thank you, Abhishek sir, and the organizing committee for inviting me in this session and giving me this opportunity. So, let me share my screen. Is my screen is visible to everyone?
Yeah, it's visible.
Okay, so this session is about some practical aspect of the deep learning and image processing, and we'll be also executing some Python codes. So let's start with that. So this is our brain. So our brain has several parts, and all of the parts has their own responsibility of thinking logically or emotionally or storing the information as a memory. But the most building blocks of the brains are neurons, biological neurocells, and this particular cell has some special feature. It can process information. Now, these cells has regular cell body structure, but there are some additional branch-like structure it has around the cell, which we call dendrites. And also there is a tail-like structure is there, which we call axon. And at the end of this axon, we have branch-like structures, which is called axon terminals. And now these dendrites has special feature which collects information from another neuron cell. And then after processing the information in the cell body, and some part of the processing is also done on the axon, it transfers the information to another neuron cells, and that is how it makes a huge and complex network of biological neuron cells. And this complex huge network is responsible for all our thinking process. Now that is the sole idea behind the neuron, designing the artificial neuron for solving the problems that is being solved by the human. So you can see in the screen there is a architecture of the artificial neuron, where the values that is present in the x1, these input values, that is x1, x2, x3, and xn, these are passed inside the uh, artificial neuron, and it is first multiplied with some weights and then passed inside the transfer function. Now usually this transfer function is nothing but a linear function. So to bring some non-linearity in the system, it passes this output of the transfer function to activation function. Now this activation function, which is a nonlinear function, processes the information and throws an output, which is again used as an input for the next neuron. So let's compare both the architecture, both designs side by side. So we see that there are dendrites which receives information, which is similar to multiplying the weights and transferring that value to the transfer function. Now cell body is compared with the function, transfer function. Now here you can see that transfer function is nothing but a weighted sum, and along with it there is a b term is coming. B is nothing but just a bias term. Bias is added, and then the entire thing is passed to the activation function. Now activation function adds the nonlinearity, and then it throws the output, which goes to the another neuron. Same thing like the axons do. So there is a similarity between the name also. Here it is axon, here it is activation function. So it is good that one neuron works like that. But as I said, that brain is a collection of huge billions of neurons. So similar kind of thing are done here to construct a neural network. So uh, when we are constructing a neural network, we are actually using multiple, maybe not only just thousand, maybe millions of neurons we are actually using. Now, before going into the structure of the neural network, let's have some idea about the terminology. So whenever a neural network is presented in this form, the leftmost most side is called the input layer. And remember, this input layer is not neurons. These are just input values, just float values or values, numerical values only. And the rightmost layer is called the output layer. And this output layer, unlike the input layer, are actually neurons. And between input and output layer, there are hidden layer. Now, in this particular example, I have chosen one hidden layer, but there could be multiple hidden layers. Actually, there are more. The more the hidden layers, the more the neural network is better. So, hidden layer also consists of neurons. So let's look into how this works, how the communication between the neurons works. So first, when some data is used, say x1, x2, x3 are the data which is passed into the neural network. First, three weights are multiplied and each with one data. Then we get this linear equation of x1 into w11, x2 into w12, x3 into w13, and b1. B1 is the bias term. Bias term is added. It is kind of you can think of as a intercept in the linear regression. So those of you who have idea about linear regression, they know that there is a concept of intercept which is independent of any variable term. So to mimic that idea, there is bias term is added. Now entire thing is passed inside the activation function, and that is the output of the neuron. Similar thing we are doing for the second neuron. Here the input data remains same, but the weights gets changed. A new set of weights come into play, and the bias term also gets changed. Similarly for H3 and H4. Now in the output layer, when it could be output layer or it could be the next layer also, next hidden layer also, here the inputs getting changed. The same x1, x2, x3 is not going to be an input, rather the output of the hidden layer, that is h1, h2, h3 and h4, is going to be as input for the O1 neuron. And as usual, a new set of words is going to be assigned here along with a new bias term. So similarly, neuron 2 or output layer neuron 2 is also designed. Uh, Pardon me, I forgot to keep the activation function here. But all these linear weighted sums will further be processed by the activation function. So this is how the entire neural network is designed. This is very simple architecture, but the original neural network architectures are not that simple. It is much more complicated. Now there is a concept which is called fully connected layer. Now if you look into this uh, hidden layer, and if you look into the input layer, any two pair of nodes, if you choose, you can see there is a connection between them. So if that happens, then we call that layer as fully connected layer. Similar to the output layer also, because the output layer is receiving the input from the hidden layer. And since the output layer is receiving the input from the hidden layer, and any two pair of nodes you choose from the output layer and the hidden layer, and if they have connection, then we call it fully connected layer. So this layer is also a fully connected layer. Now let's calculate how many neurons, by the way, neurons are also called perceptrons, are there in this particular network. So as I mentioned that the input layer is not a neurons. If this kind of diagram is given in the exam, you will never count the input layer nodes for the neurons. Then every every neuron has their own bias term, and they have exactly one bias term. So the number of bias term will also be same as the number of neurons. So we'll have 6 bias terms for 6 neurons. Now let's calculate how many weights we have. So 3 input nodes were there and 4 hidden layer nodes were there. So total 3 into 4, 12 weights will be there. And similarly, four hidden layer and two output layer. So 4 into 2, 8 nodes, 8 weights will be there, and total there will be 20 weights. Now, what is a learnable parameter? So these weights and the biases, they are not an input value. They are assigned by the neural network itself, and that is why they are optimized using a optimization algorithm. When we will be training a particular neural network, we are by training we mean just to update the values of these weights and biases. So in that case, we had 20 weights and 6 biased terms. So we have total learnable parameter as 26. So this is one example. You can just try it at home and check whether everything comes according to the formula or not. This is just for an example. Okay, so this is actually a brilliant idea to mimic the human brain itself. But what guarantees that the human brain, this mimicking idea of human brain, will actually be useful, will actually uh, can do any kind of work or do any kind of prediction? So that is where there is a very famous theorem called universal approximation theorem. I'm not stating the statements here, but I'm just giving you the idea what it says. It says that if we have enough neurons for a problem in a neural network, and uh, the problem can be thought of as a function which is going to be continuous. If it is continuous, in that case, there there exists a neural network with enough neuron that can approximate that function. This is the universal approximation theorem. This theorem actually supports the neural network idea, but there is some problem also that it may not be very easy to find such neural network. Also, it may not be that fast, or it may not be practical also. So some of you may be from computer science background, they know about there are two types of problems. One kind of problem is NP hard. So those problems are also kind of not able to solve by the neural network itself. So it is may not be always practical. Okay, so let's look into the deep learning applications. Now, most of the applications or most of the problems that we solve through the deep learning or machine learning, they fall under broadly two categories of problems. One is classification, another is segmentation. So the classification is nothing but just detecting an object from an image. So the answer or the solution will be whether there exists any the object exists in the image or not, in terms of yes and no. That is what classification is. While segmentation not only stops by answering whether it exists or not, it also fetches the region of the object. So let me give you some examples. So it's a very famous example given by cat and dogs classification. So if you have a neural network, and that can tell you by looking into the image whether it's a cat image and whether it's a dog's image. I'm assuming there is only one animal in that image. Then is actually solving the classification problem. Now look into this image where the designer of the architecture is not interested in whether cars are existing or not. He is interested in the region that is occupied by the cars, the region of the image that is occupied by the cars. So this kind of problem falls under category of segmentation. There are a huge area of application in real world, as Dr. Bhaduri was mentioning that healthcare, which is our research area, where we work on medical images, we apply deep learning there to figure out existence of any tumor, any abnormality, or any disease. There are other areas also like social media, like security surveillances, document digitization, for example, documents that are written in hand or printed in an old printer, digitizing them, disaster prediction, and agriculture. Okay, now enough of the theory. Let's look into some practical image processing and the problems with deep learning. So we have an image, and now we have to pass this particular image into a neural network. Now, already Dr. Bhadri mentioned that the images are nothing but a 2 or 3 dimensional matrix, and particularly if we are working with a color image, that means it's a 3 dimensional array or matrix where there are three different intensity of image, from red and from green and from blue. They three of them composes and gets you the color image. Our human eye is not able to distinguish between whether it's a real color or it's a combination of red, green, and blue. But the this is one of the efficient way of combining of presenting the color image. Now, this image is split into three different parts, three different channels. Now, each of these channel is of 1080 or cross 1080. That means they have 1080 rows and they have 1080 columns. Now, let's calculate how many pixels are there in this color image. This is a simple color image, but if you calculate the pixels, you multiply 1080 into 1080 into 3, you get around 35 lakhs of pixels. Now, when using this image in the neural network, the number of input layer jumps to 35 lakhs. Now, when number of input layer jumps to 35 lakhs, for each input value, there are weights. There are multiple weights associated, and for each of these hidden layer, there is a connection to the output layer also. So altogether, total number of biases and weights will increase in multiple terms of the input nodes. So it will be around 100 times of the 35 lakhs. So it will easily cross 10 crore or 35. It will go around 20 to 30 crores of weights, and this is actually a big problem because uh, training that huge number of parameters is almost impossible for the computers that we have in our home. uh, GPU do have some ability to compute that kind of uh, model, that huge number of parameters, but still this is very huge. So what are the solutions? So there is one another problem also. For example, if you look into the face of an elephant and if you look into the face of a tiger, you see there is a difference between the position and sizes of eyes, nose, and ears. Not only the position, not only the size of eyes, but also the relative size of the eyes, nose, and ears. So this kind of information are called spatial information, which is lost, which is not processed using this raw neural network architecture. So what to do? To rescue us in this problem, we have got the idea of convolutional neural network. It is true that neural network already got designed long term back, but not much work was done on that. After convolution neural network was introduced, neural this training of images using AI on image, on sound, on text became very rampant because of the easy features of convolutional neural network. Now, as machine learning, when we are doing machine learning, we do extract the feature manually. We can automate a code, but the model itself doesn't extract the feature. The same idea was for deep learning when it was we had neural network only. But when convolutional neural network came into the picture, the feature extraction part of the problem also became the integral part of the model itself. Now, just for an example, we have four types of bikes, motorbikes here. Now, if we want to classify which type of motorbikes is each of these, say one is bullet, one is scooty, one is sports bike, another is utility, what we will be doing as a human being, what we will be doing? We will be looking into the wheels, we will be looking into the oil tanker, we will be looking into the seats, silencer, and the headlights. We will look individually in this each of these uh, part of the motorcycle, and then we can identify, okay, this is either a bullet or a scooty. Now what if you get an algorithm which does the same for you, but it does the same thing without your intervention and automatically? So for example, if the bike wheels are chosen automatically, the seats are chosen automatically, the headlights are chosen automatically, then it will be very easy for the model to process that information and predict whether which bike is of which category. Now, to solve that problem, we got convolutional operations. Now, these convolutional operations are mathematical operations, but originally it was used for sound processing, and later some scientists found that these are very helpful for any kind of uh, data processing, and they introduced in the neural network. However, you don't have to worry about these complex formulas. It is very easy thing. So let me give you one example. Now the left hand side image you see, this is actually a image, sorry, the left hand side matrix you see, this is actually a image matrix, and in the middle you see a 3 cross 3 smaller matrix. We will be calling it as filter or kernel, and at the right hand side this is the resulting matrix. We will be calling it feature map. Now each of these 3 cross 3 sub matrix or sub arrays of the image matrix is dot product with the filter or the kernel matrix, and then the dot product value is placed in the corresponding location of the feature map. So that is how we calculate the convolution. I will show you one animation video. It will be very much clear with this video. So this 10 minus 1 10 minus 1 10 minus 1 filter or kernel is multiplied with every 3 cross 3 submatrix, and their value is placed in the feature map matrix. Now if we have multiple filter kernel, then we can actually calculate multiple feature maps using this. Now here we have image uh, of a dog, and we see that using some convolution we got 8 in different feature maps. You can see the each of these feature maps highlight a particular information. For example, the first feature maps you see, this highlighting the grass area around the dog. The second one also highlighting the grass area around the dog, but the first one is having the rope of the dog also being highlighted. Now, if you look into the last and third last image, here you see the dog area of the image is being highlighted. If you look into this middle feature, you see the only the age information is being highlighted, nothing else. So each convolution feature actually gives you some kind of information. Here is another example. So there is a concept of high level feature, mid level feature, and low level feature. So in high level feature, we get more of a age information or a independent object wise information. While when we go from high level towards low level information, we get to see con- the the texture or the orientation, that kind of information uh, is retrieved from the low level features. So here you can see there is a headlight. The headlight of the car is being filtered out. The window of the car is being filtered out. The wheels of the car is being filtered out. So this is how some of the features are captured using the convolutions. Now let's go back to our old problem of processing an image in neural network. So earlier we saw that we have around 35 lakhs of pixels. Now if we train it with one hidden layer, a network just with one hidden layer and 10 neurons in the hidden layer, we get to see almost 3.5 crores of weights and biases going to be optimized. Now, the same thing if we do for a convolutional layer, what we have, so if we have 10 convolutional maps, now this 3 cross 3 filters. So as I was saying that instead of entire image being trained, entire pixels of the image being trained, now in we only be training this particular 3 cross 3 submatrix or this 3 cross 3 filter. These weights will be training. So here the number of pixel drastically reduces to only 9 weights for each of these convolutional filter. So total we get around 932 learnable parameters, which is drastic reduction from 3.5 crore to around 1000 parameters. And that is the reason, that is the sole reason, because the neural net, instead of raw neural network, convolution neural network is so much popular. Also, it is also in we are just assuming 10 hidden layers and 10 convolution. The real life problems are not that simple. We used to use more than 10, more than 100 hidden layers neurons and more than 10, maybe more than 1000 convolutional filters. But whatever be the way we calculate, the number of learnable parameter reduces significantly. Now, this is one example of a convolutional neural network where we are passing handwritten numbers into the neural network and it is actually detecting which number it is. So it starts with a very high level information, high level features. You can see there are 6 features are being captured from that image. Then it captures some mid level features and then it goes to low level features. And finally at output layer it predicts what number it is. So here, if these convolutional layers, these are hidden layers, and within this hidden layer we have high level, low level and medium level features extraction. Okay, so there are some popular architectures of convolutional neural networks. One is ResNet. ResNet is very much used for classification type of modeling. Here there are different convolution layers have been applied. These boxes are nothing but convolutional operations. Another is vision transformer. Vision transformer is very popular nowadays. It actually uses one idea that it breaks the input data into equal sub data and then passes the data independently to the neural network. So this also uses some convolution neural network and it is also used for classification. Then as Professor Bhaduri was mentioning that YOLO, which is used for getting the bounding box around the object for object detection. This is the architecture of YOLO. And this is one neural network, one convolutional neural network for segmentation task, and this is widely used in medical image segmentation. And UNIT is most popular segmentation architecture right now in the market. Another is SageNet. SageNet is a little bit older model, but before UNIT was introduced, it was used a lot in every aspect, in medical imaging also, also in other type of object detection. So let's go to some, and let's do some coding right now. So uh, so uh, we will be starting with some codes. We will be doing it in Python. I have just shared the link of the folder of Google Drive folder. You can download the code. Those of you who have logged in using a laptop or desktop, you can work with me also. Or those of you who have joined through mobile, they can follow me. So this is a Python code, and in Python we have some predefined libraries that we load for our work. And some of the predefined well-known libraries for image processing is CV2. CV2 is nothing but OpenCV2. It's a very famous library, and NumPy for numerical operations. NumPy is used, and Matplotlib is another uh, library which is for plotting purpose, plotting a image or also plotting a chart. You can use Matplotlib. Now here I am reading an image. Now most of the codes are already executed, so I will just walk you through the codes. In some cases the code may take longer period to execute, so I thought it is better to execute it before. So now once the image is read, the image is read using the imread function of a of CV2 package, and you have to pass the path of the image. Now once the image is read, you can get the details about the image. So type is a function that gives you the type, what type of data it is. So this is numpy nd array. That means it's a numpy array. Then shape of that image is says that what is the dimension of the image. As I already showed you in the slides that it is a 1080 cross 1080. That means height of the of each of these images is 1080, width is also 1080, and there are three channels, each of each from red, green, and blue. And D type means the pixel values, what kind of data object it is. It could be float, it could be number also, it could be integer. So what kind of it is? So right now it is actually integer, because the values that ranges from 0 to 255 for every image, the except medical imaging, for normal natural images, the values they range from 0 to 255. Now using one of the matplotlib's function, we are actually plotting the image. So we see this is the image that we are discussing. Now we wanted to check what is the matrices of each channel. So this particular is a red channel, this particular image. So this is the blue channel image, this is the green channel image, and this is the red channel image. But these are the matrix, how I can see them, how I can see what is the red image, what is the blue image, and green image. So there are some codes are there where we are extracting the blue channel image and the red channel image and the green channel image here. And if we plot them, we get to see this kind of image we get to see. Now, for understanding purpose, I have just plotted them in a green, blue, green, and red. But ideally, they do not look like blue, green, and red. If you are plotting an independent image, single image, one two-dimensional image you are plotting, it will come as a grayscale image. So in this code, we have just plotted the actual blue filter image, actual green filter image, and actual red filter image. Okay, now let's do some transformations that Dr. Bhaduri has just discussed in his session. So there is a function, this is a user-defined function which do fast Fourier transformation. Then there is a function, this is actually for cropping the image, and why we are cropping, we will be discussing that. Then there is a function called FFT reconstruct. That means if you have already converted an image to a Fourier domain and you want to get back the original image from the Fourier domain, this function is written for that. And this function actually calculates the magnitude of the uh, values that is obtained after the transformation. Now here we apply all the things, and uh, we actually cropped the image in three different uh, boundaries. You will see. So this is the original image, and this is the image after Fourier transform. Now we are taking the image, we are cropping the image only up to 50 pixel from the center, 50 pixel from the center, and look into the reconstruction of that particular image. This image becomes very much blurry. This is the original image and this is the reconstructed image. So as you see that 50, if you just take 50 uh, pixels only, uh, 50 cross 50 image from the Fourier transform center, then the image may not be that much clear. The image will not have that much clarity. Now we just increase the value of the radius. By radius I mean the distance between each of these sides from the center. So each of these sides will be 2 into 100, that is 200. So in that case, you see, we get slightly better resolution of the image. Now when we do the same for 150, we get much better resolution. Now we do for 200. Now it almost look like the original data. You see, it almost look like the original data. So this is a very useful technique to compress an image. You can compress the image just by one, I think one 100 times of the original image by number of pixels. Okay, so now there will be another feature extraction method, which is wavelet transformation. Using wavelet transformation, what we get some edge information. So you can see this original image is done wavelet transformation, and we get the horizontal edges. This actually gives us uh, four different images, and this is the horizontal features or horizontal edges are extracted in this horizontal feature, and then the vertical edges are extracted, and then diagonal edges are extracted. Now it may not be visible in the naked eye, but if you can try at home and you zoom in, you can see that slight lines are visible. For example, this person's hand is diagonal. It is along with the diagonal only. If you look into the image at your home, if you run the code, you will see there is a slight line is coming along the diagonal, which is the hands line. Now we will be now showing some of the filters in, but because filters are very important in convolutional neural network also, because filters do fetch some information also for downsampling a data or upsampling a data. Filters are used aggressively. Now we have used some of the filters here. Let's see what kind of results we get. Now this is the original image. We get the minimum filter. So by minimum filter means we consider 3 cross 3, 3 cross 3 submatrix, and compute the minimum value, and then replace that minimum value in the feature map. So by that way we get the minimum filter. So this is the original image. if you get the minimum filter, you can see this is darkens little. Why this is darkens? Because uh, from 0 to 255, when you go towards 0, the image, the intensity is goes toward darkness, and if you go towards 255, the intensity go towards brightness. That is why the min filter always darkens the image. Here is the max filter, which is the opposite. You see that the original image is looking like little bit dark. So max filter actually enhances the image, enhances the uh, brightness of the image, and the average filter is actually blurs the image. So as you can see, this is the actual image, and you see this is the average filter. A little bit resolution is lost. Now again, there are some other filters. So this is the original image. Then we apply Gaussian filter. You see, slight random noise has been introduced in the filter. It is not as clear as the original one. Again, Sobel, there is a Sobel filter for vertical and Sobel filter for horizontal. This is also extracts age information. You can see the vertical lines are very much clear, while the horizontal lines are much clear in the Sobel horizontal filter. We just tried with another image, the same Sobel filter we applied using another image. Here you can see that vertical lines are in most of the lines here are horizontal, so the image doesn't look that there is much to see. But if you look into the horizontal Sobel filter, you get to see a lot of information here. So this is uh, about the classical part of the of the computer vision. Now let's look into the one of the deep learning part of the computer vision. So as a part of our research, we are actually working on brain tumor segmentation, and to do that, we are uh, using some brain MRI scan data. Now, there are some data available in open access, and most famous of them is BRAT's data. We have used that BRAT's data and we have trained a model. So these are the important libraries that we use. Now, this particular code is for a variant of UNet. So as we mentioned, there are UNet is the most important segment, most important architecture for segmentation purpose. This is the code for that. Now, uh, this is the performance matrices, and this is the plotting image, plotting function, and we are not worried about it actually. These are some data processing functions, and this function actually uh, does the prediction part. Now, in this case, in this code, we are first uh, using the model of NN unit. NN unit is a variant of unit, but for the timing, you can consider it as a unit also, where we are passing the input channels and the output channels. So, what are input channels? I will come into it shortly. Then model part. So this is already a pre-trained model we have stored in one of our memory location, and the model weights. So remember the learnable parameters, that weights and biases are the learnable parameters. Those weights and biases get stored in a file called PTH file. And after training a model, every time if you use the PTH file, you can get you can use that model using this PTH file. Now there is a image directory and there is a mask directory. Again, I will tell you what it is. So look into these images. So this is a brain MRI scan. Now MRIs have different types of scan. For example, in some MRI, the water part comes more. In some MRI, the water part doesn't get highlighted. So there are different modalities. So two modalities we have passed. Since two modalities that we are passing, we call that input channel equals to 2. And we are actually predicting the tumor region. But tumor region has three different parts. Some is core tumor region. There is outside region of the tumor where the cancer cells are present, and there are boundary of the tumor. That is what we are actually presenting. You can see also outside the boundary of the tumor there are some white area which is water area. So we are predicting all the three regions. That is why we mentioned that in channels will be three. Now this is one of the model output here after training. Let's look into another one. See, this is the MRI scan, and our model is accurately predicting the tumor region. See, there is a small region, but still is being predicted by the. So you can find this code, and also some sample data is available in the Google Drive link that I shared. And here are some reading resources that you can use for further enhancing your knowledge. Thank you.
Thank you, Shankar. So there might be a lot of queries or questions. So may I first request those who are in online using YouTube or maybe using Google Meet, they first ask the question. So the participants who are using their YouTube or they're using their Google Meet are requested to type the questions on the chat box so that I can convey this message to him. Or you can unmute yourself, those who are in online mode using this Google Meet. Okay, so I get one question by Alika Mukhopadhyay. She is saying that, can you please explain the UNet architecture you used in some more details? How is it different from the original UNet architecture?
Sure, sure. Let me reshare my screen once again.
Yeah. And Shankar, you have plenty of time now. So the next session
Yeah.
is 8, so you have plenty of time to explain things.
Sure, sir. Sure. Okay, so all of you can see my screen? Okay. So in the UNet architecture, what happens is there is one channel, there is one image is passed, or maybe whatever number of images passed. It first converted into 64 feature maps, then again it converted into another 64 feature maps. These 64 feature maps is further down sampled. That means the image is just reduced to half by each dimension. So if it's a two-dimensional image, half by each dimension means that is reduced to one-fourth of the image. Anyway, then again further 128 features is extracted from the same image, and so on. And then at the end, at the last level, when the image is reduced to a much lower size and it doesn't make sense to reduce the size further, we start upscaling the image. And while upscaling the image, we concat each of these feature maps that we extracted in each stage. For example, if the image is upsampled and in this stage, then this feature map that you see in the third stage is concatenated with the upsampled image. Then again some feature maps are calculated, and again the image is upsampled. So that is the plain UNet architecture. But the NN unit architecture that we mentioned here, this is as architecture, this is exactly same. There is no difference in the architecture. But if you go inside the architecture, there are convolution layers. You can see, if you can look into the codes, so you can see there are convolution layers. Then there is a normalization layer is there. Then there is the activation function is being applied. This activation function is called leaky ReLU, and the normalization is instance normalization. But in regular unit, we use batch normalization. So batch normalization is nothing but when we train the model, we pass the model in different batches. If we it is actually helpful, because if we pass the entire data at one stage, this will be a overload to the system. Or if we just pass one by one data, then it is becoming very slow. Every iteration will become very slow. So in order to get rid of that, based depending on the power of the computer, we pass the data by batch by batch. So batch normalization was happened when entire batch was normalized. But here instance normalization is happening. That means one particular image is being normalized independently. So that is the difference. And then leaky ReLU is a different activation function other than ReLU. ReLU was being used earlier, and till now ReLU is most popular. But some of the researchers found that leaky ReLU is very useful. In using leaky ReLU is going to be very useful. These are the only two difference between unit and NN unit. I hope this answers your question.
So, if Aleka, are you happy with that? If you have further questions, please do not hesitate to write it on the chat box. I will again share with Shankar. So, there is another question by Hilal Ahmed. His question is, why are deep learning model often considered black boxes, and what makes it difficult to understand their decisions?
Yeah, it's a good question. So deep learning models are considered as black boxes because, sorry, yeah, deep learning models are considered black boxes because, as we mentioned, that there are several feature maps are being generated. You can see in in this data also. You can see there are at first layer only. You can see six feature maps are generated. But if you go further deeper, then it is very difficult for a human being to identify what feature map is useful for what purpose. But the computer understands it, and that is why we data scientists, we do not delve into the feature maps, what kind of feature maps the architecture is generating, but we just define the number of features that has to be generated in each layer, but not, we do not look into the features. That is the reason actually it is called a black box algorithm. It is something like the computer learns on its own.
Okay, if it's not yet clear, so please don't hesitate to write it again on the chat box. I will again convey the message. Another question is, can the model take all the cross-section images of the MRI in input layer for predicting the 3D position of the tumor?
Yeah, this is possible, but for that you need a powerful GPU. So we actually tried this one. We tried 3D modeling, but we are not able to do because we had 16 GB of GPU, and to build a model using a 3D or the kind of data size we had from BRATS, we needed at least 24 GB of GPU. So if you have enough GPU, you can surely build a model. You can really pass the entire 3D data itself at each iteration.
Okay, then another question. Again, if it's clear to you, it's fine. Please write it on the chat box. And if not, then again, write the question. Again, the question by Orchana, she says that, sir, can you please explain why cleaning and filtering is important while doing further processing?
Yeah, so usually when we are actually using deep learning models, we do not need to do any further data cleaning or data filtering operation. The deep learning model itself does that. How it does that, as I was explaining, so these are the, you can see these are the filters, or these are the kernels. They do some convolution operation and generate the filter. Now, all the filters that we have discussed, they are doing the same thing only. They are doing the same thing with the images. They are actually doing uh, generating some features. So, if that filter, that particular feature is important, the convolutional neural network has the capability to optimize the kernel or optimize the weights in such a way that that particular filter will be automatically generated. But if you have some prior information, say we are working with some horizontal the data, and we are trying to capture some horizontal information, then before training the model, if we just use the filters and extract the horizontal informations and then pass those information to the model training time will be reduced. It will be useful for the model, and the model will be much more robust in that case. But
Again,
again,
yeah.
sorry.
Oh, so please continue. Yeah.
Yeah, but again, that is dependent on case by case, the kind of problem you are solving. And in data science also, there are the problems we solve. It is typically focused on the uh, problem we are solving, and we take the approach. So it falls on that what kind of problem you are solving. Yeah. Sorry, sir. Sorry to interrupt you.
No, it's fine. Uh, Again, it's with the in continuation of UNET regarding Aleka. She says that I understand how much improvement was there in the output results after these changes regarding UNET that you mentioned about.
Yes. It increased the performance very in huge margin. So earlier, if the original unit was giving 60% accuracy, now NN unit gives around 76% accuracy on same data, same number of training epochs.
Okay, Aleka, if you have more questions, then you are welcome to write it down here. Another question by Archana, sir, is it possible to detect the image through the raw neural network, like you have mentioned, that it is the thing that leads to the convolution network, neural network? Can we recreate raw network?
Yeah, certainly. If you let me show you one thing. Yeah, you can see. So if you print the model itself, what you see, you see the entire things that you have. Now there are right now I don't know, but there are some codes are there which, if you pass the model, it will give you the raw neural network, that is being used underlying this convolutional neural network.
So if it's clear to you, please write it down, or you can again ask question. Uh, Another question by Ravi Misra. Can you explain how KAN is different from MLP?
Sorry, KAN by means?
Okay, can Ravi, can you please write the full name of KAN? Okay, might be is writing. Then I will again come to it. Archana says, "Sir, will the noisy data depends on the processing of feature map?"
Uh, it actually it depends, but if you are using, again, if you are using uh, deep learning or convolutional neural network, it doesn't depend that much, because that neural network has the ability to extract that information.
Okay, so if it's clear, then it's fine. Otherwise, please write it down. Again, there is another question. How do you choose filter or kernel? Is there any process behind it?
Yeah, that's actually a good question. So that is the sole purpose behind the training. We When we train the model, this kernel or filters, the value inside this kernel or filters, they get optimized once you train the network. So you will be so along with this code, you have to, if you are actually training a model, then you have to use a optimization algorithm. So we usually use, there is a optimization method called adam, there is something called sgd. So any of the optimization algorithm, if you use uh, these optimization algorithms, they only train these models, these weights get updated, or the values at the kernel, they get updated.
Okay, I think that's also the answer for this question. Sir, can you mention any one of the models? I think that gives you the answer. Okay, again, another question regarding the unit architecture. Is it definitely a good improvement from about 60% to 70%? What next steps are you planning for further improvement of the output accuracy?
Uh, yeah, actually, there are some other aspects of the deep learning architectures. Uh, One of the most important thing that recently in news is mm, the one that was I was discussing, that transformer architecture. Now, transformer architecture is enhances the accuracy further. Also, there is a thing called attention-based mechanism. That means instead of processing the entire data, the model, the deep learning model itself learns the attention. So there are some other features that we are working with, we are um, trying with, so that we can increase the accuracy. But so far, we have already experimented a lot of things. We find that NN unit is the optimized. NN is the optimized for segmentation.
Okay. Then Ravi mentioned about the full form of KAN is Kolmogorov-Arnold network. So his question
I'm
was,
sorry.
okay,
Sorry, I'm not aware of this one.
okay, so fine. Uh, so if you have any further question, please write it on the chat box of YouTube. I have some questions regarding from Google Meet link. So its question is whether all the codes can be run in a normal laptop or do we need a GPU machine?
The first code that I showed you, that is MSAST CV workspace, this you can run in a normal laptop, but for the unit code, you need a GPU.
Okay, another question from Rigom. Sir, from a filtered image, can we restore the original image using similar model?
No, it is not always true. It is something like if you take the average of 10 values, then from the average you are going back to the original 10 values. So it is not always possible.
Okay. So any other question? So some of the links, they want the YouTube link. So could you please, those who are in YouTube link, could you please share or send me email, or you can share your email ID here, or you can directly send me email here and just write it down. So that I can send you the link here. The codes are available in the Google Drive link so that I can share with you. So those who want this link, can you just send me email so that I can just mention on the subject that you want the code for the presentation, so that I will also share the link with all of you. So any other question or comments? It's been excellent. So just few. So you are currently from your service life in industry to now you are again moving towards academia. So the question is, so you have both the experience with all of, I mean, both the situations. So how do you feel that, or what could be the motivation, or what could be your suggestion to the students, that those who are going for this data scientist, they are aspirant of data scientist, or their dream is to become a data scientist in near future. So what could be your suggestions to them so that they can fulfill their dreams?
I would say never stop learning, or never reduce the appetite of learning, because that is the only thing matters. If you are going to corporate sector, and corporate sector is a very risky sector actually. So here, new technology will come, and it might be a risk to the job we are doing there. So uh, even if it is data science field, there are very few people are there in corporate who do really know the data science very well. So I would say first few years of your career, start focusing on the learning, and then you don't have to worry about your career growth.
Okay, great. So maybe another question could be so here we can see that many students are from math, stat, or even engineering background. So what are the most essential things that one should have to become a data scientist?
Mm, the idea of the thinking analytically, or say thinking, mm, looking into a data, and understanding the data, that is the ability that data science demands. So to inculcate that kind of ability, I think practice is the only key. I mean, if you do practice continuously, then definitely you will inculcate that kind of ability. And for job purpose, the managers, the supervisors mostly will look for business knowledge along with the technical knowledge. So it is better to, along with studying data science or studying statistics, machine learning, if you can also study what is the purpose of using this, that the techniques you are learning, then it will be very helpful for your career growth.
Okay, so another question by Orchana is, sir, how can we develop our analytical skill?
It's fully by practice only. Uh, I would say there are some case studies available. There is a book, by the way. I will share the name with you. So that book actually shares some case studies. So if you look into those case studies, then you'll be able to understand how business problems are solved. In typical business management courses, this is the way they teach. They teach how to solve a business problem. So if you just study some of them, you will get the idea how to approach in a business problem.
Okay, so any further questions? So those who are in Google Meet can open up, can directly ask questions without writing, or those who are in YouTube can again type. So some of the requests are like, can you share a few links of the good books so that they can start with? Like, what are the programming languages or from where they start? Because few of the students who are from basic maths background, they may not have that good understanding of programming, what exactly they work and how they work. Or maybe they do have a good foundation on linear algebra or analysis, how this can also be useful. Can you give a brief idea about that? That might be helpful for them also.
Sure, sure. So um, for programming, there are some very well-known websites out there, which uh, I actually forgot the names. I used to follow those websites for programming skills, and nowadays the one of the most important thing that have came, that ChatGPT. You can use ChatGPT for programming solutions. Yeah, LeetCode is a programming website, and Kaggle. These you can use for practicing your programming skill. And those of you who are actually from linear algebra background or mathematical background, I think uh, for you, deep learning or AI is going to be very easy, because deep learning and AI are mostly based on the linear algebra principles. So uh, I will share maybe by today only. I will share some set of books with sir, and sir can share them with you.
So sure. So any other questions or comments? Yeah, is there any application of topological data analysis in image processing? It's by
Uh, not yet sure.
Okay. So what do you mean by topological data analysis? Might be, I'm not sure about the term.
I'm also not sure.
Okay. Yeah, any other question? Okay, then it's a really a very good and very nice interactive session. Those who are in YouTube, they are also equally quite like they're equally able to ask questions, and we are very thankful to Shankar for very patiently he listened all the questions and gave all the answers. It's really a very informative lecture because he has given many links. So those who are in YouTube link, just send me email. I have already shared my email ID with this chat. And one more thing, I must say that after this 3-day workshop, at the end of the last day, we'll conduct one exam. So those will be obtaining 50% of more than 50% of the score. They will certainly get one completion certificate. So I request all of you. So I have already shared with all of you the attendance link. So that attendance link are available on the chat box. So please have a look at that and click on that and fill it now. Those who are in Google Meet link and also have a look at the YouTube link. There you will find the link for this attendance. We will provide certificate to all the significantly attending participants. They will certainly receive this, receive the participation certificate, but a special certificate for few of them will be issued who will be completing successfully the workshop on data science. For that, we'll, as mentioned, we'll conduct an exam. So it would be 10 questions. It would be a multiple choice question based on the whatever are being taught during these courses. And those will be obtaining more than 50% of that will certainly get the certificate. So with that, let's thanks once again to Shankar for his nice and wonderful presentation. And
Thank you, sir.
yeah, those who are in YouTube link, I already filled. So yeah, those who have already filled the this form need not fill it today, but tomorrow you can certainly fill it for the next day session. But for today, one attendance is sufficient from each email ID. Okay. So thank you very much. And we'll conclude this session.
Yes, can everybody hear me?
Yeah, perfect. You're
Perfect.
yeah.
Was there any hand up that I saw?
No, I think by mistaken, someone has raised her hand.
Okay, okay. I'm so very honored to be chair of this next technical session. And my name is Christina Trell, and I'm a medical doctor and specialized in infectious diseases, in which area I also did my PhD. But I would like to start by presenting my father, who is going to have the first talk of this technical session. And the title is Back to the Future of Natural Structures. And my father is Eric Trell, who is emeritus professor at the University of Linköping in Sweden in family medicine. And he started all the way back in 1968 and finished his PhD in 1972 and became a professor in family medicine in 1986. But now we will try and give the talk Back to the Future of Natural Structures. Så, filen har jag tryckt på. Och sen ska vi webbläsa Vänta, vi ska ta här och se om vi kan. Det är den du ska ha, va?
Mm. Just. Yes.
Men,
Fine. Då är jag inne.
Men frågan är, can you see the presentation?
Yeah, we can see this very much.
Ah, very good. And then we'll do like
And
this.
Eric will have 35 minutes, and this talk would be basically a talk on the memory of Professor M.R. Odhikari. So it would be the first memorial lecture of this conference, and that would be dedicated to late Professor M.R. Odhikari, who was the pillar of our institute. So it's all yours now. So you have 35 minutes extra time.
That's fantastic.
Okay.
That's, oh, yes, then I'm on, yeah. And starting up, going back to the future, as I say. And I have been here many times before, and always went back in a way to my work that is still advancing a bit. And going back to the future will be here a historic trip, and I can show it a bit here. And it happens to be a Nordic trip because the progenitors of this field are very much from our three countries, Sweden, Norway, Denmark. And it starts really 200 years ago with Jöns Jacob Berzelius, who is generally acknowledged as the father of modern chemistry. And he invented, for instance, the modern chemical notation that is still valid, namely the first letter of the Latin word with a suffix of the number of atoms. So he's very actual here, and he did a lot of other things. He invented a lot of four elements, for instance. And the interesting thing is Sweden is very mine-rich and iron-rich and mineral-rich, and no less than 20 of the elements have been invented or isolated and discovered by Swedes, 12 of them during the golden age of Swedish chemistry, which was in the mid 18th to mid 19th century. Anyhow, he also made the distinction between organic and inorganic chemistry. So that is, he was really on the verge of formulating a periodic system, but working in those age were hampered by a lack of knowledge, lack of data. So when he died in the middle of 1800, there came another development, namely that of valence theory, because just the lack of data. Oh, is it still listening? Yes. Okay. The lack of data, they allowed and nurtured a lot of speculations about various poles and ends and channels and whatsoever in the unseen mass. And that in turn led to the present chemical notation, which is rather bewildering flora of, let's say, ball and pin and wave frame and so on, as we all recognize. But are they real, really? Yes, that's the question, but that's a passive question here because it comes more like a secondary of the results. But anyhow, when can we go back to this history? Yeah, that is with Marius Sophus Lee. And he made a thesis in 1871 om geometriska transformationer, geometric transformation. But unhappily, this was in Norwegian language, which is not very well known. And he didn't transform it or translated it to German or other languages because he was captured by his continuous transformation groups that really stemmed from this thesis, but overwhelmed him. So he spent all his continuing life with these groups, which he actually developed to enormous depth. But what he did in that thesis, that he actually created linear algebra, differential equations, and spherical geometry, because he was a geometer and geodetic, and he connected with Plücker linear algebra that actually stated that instead of the point as the element of physics, you could really take the straight line instead. And the straight line is good because that you can connect and make figures of. And So I go directly. The creator of the linear algebra is actually a historical fact, but not so well recognized. But these straight lines, they were also defined as being of length equal to 0. And that, of course, is because they are differential, they are derivatives, and connect with infinitesimal calculus and so on. And we can see here how he formulated it. So he made a difference between, because if you have a line, you have dx, d zeta, dy, you tend to draw it like a continuous line, a diagonal in the field. But he separated between the directions even on the infinitesimal scale. So actually, when he drew a line, he made one separate unit step in each direction. And soon he found a way of, so to say, portraying the space, which was, of course, then Cartesius space. And he found that when he drew such line, he couldn't go any further because he was locked in the corner here, as it were. So he had to draw it like this, and then he created a step. But he came also to the insight that if you turn this on and turn it, and that you can do anywhere here, it actually forms the cube, which was part of his game. So this is the way, and I will not do it anymore. But in this way, he could make a linear exhibition in a differential and actually also digital mode, because these are digital, these are square waves and not round waves or so. So therefore, I think there is coverage that he invented linear algebra where the line does the job, and he invented differential algebra and also differential equations, which you can draw from the prolongation of this. And he also was digital from the start, not analog. But anyhow, I can say this method could be used also in other. But what's the idea of making a lot of cubes? That's just Cartesian space, and that's an ice block. So he also came up with that spherical transformation idea, that really there has to be a complement to the straight absoluteness, and that could be the round absoluteness. And the round is also formed by the infinitesimal generators of its geometry. And likewise, they can't be drawn in one continuous line, but has to be made like this and forming this kind of structure. And that I can show here, but I won't take time with that. But thus, he found that there could be an interplay. There was not only a static ice block of the Euclidean space, there was not only a round figure, which actually wasn't formulated at all at that time, which didn't do anything but being round, but there was a kind of transitional space to make a phase transition. And that we must remember that actually the Lie algebras originally is about the distinction and interplay between a cubical and spherical space. It's the absolute extremes of this geometry. And if we go on like this, of course, if you can combine the one and combine the other, you can combine the two, and thus creating geometrical structure, as it were. And if we see here, this is a space frame structure, which is an octahedron, only half here, and a tetrahedron in the flank. So it's called octahedron, tetrahedron, space frame or truss. And you see here, this is the what's inside, and that's a wave, you could say. And this is what is outside, and this is a package. But how to obtain it in practice? Because these lines just go on to the early universe, which they contour. And yes, you have to have another situation where these tangential, as it were, combinations, because they can only be half. And these are the complex cones and so on. This is a lot of algebra in that, but this is a half, and this is a half also. And if we see how they are combined, when actually the possibilities came, namely when the original universe got to the astrophysical situation after billions of years. So if they met contralaterally, they would fuse to a wave package. And that's interesting. Wave packets, of course, were in the beginning of the 19th century and still very actual. But here we have a physical wave package. And we can see that analogous could happen with if just the volume, the package met, it could form an equal volume but empty. And likewise, if only the waves met, they could form just this kind of vortex but isolated. And if they met ipsilaterally, then they would, so to say, fracture into their constituents, and that would be either straight lines or just waves like zigzag. And thus we have also the generation of neutrinos and photons. So we have the whole iconography, you could say, of the space in a very easy combination of the straight line here, the linear algebra. And I show it just in the case of the wave packets, the physical wave packets, that when do they get produced? In the early universe, of course, sometimes they confront and collide and so forth. And so we have a little fraction of, you could say, mature particles. But to really confront and meet, they need this stellar cataclysm. So actually all matter we have are created, and we know that in stellar processes, astrophysical ones. And their predicament, because they are the only thing that constitutes space, is to fill up space then. And if they were just left in this order, they would soon jam. So there would be absolutely impossible situation. They must find an order in which they can continue to pack in a hierarchical way. And that is where the Bohr, Niels Bohr, Aufbau system comes in. Because this is actually something that you can pack and form parallel epipeds and then pack them in turn. So you have all the material for the successive hierarchical build of space, which is occupied only by itself. Then you can do a lot of other things. You can have other geometries there, but they still operate in that, you could say, frame space of straight versus round. Now, this is the bottom plate, And of course, this is a double thing. So they have a complementary roof space also. So in order to just show how they will look, we have the roof and the frame. They will form like modules, as I call them, because they are combined by wave packets and other things, neutrons and so forth. And so on. I don't go just to come to the to the results, but we can perhaps see that this is, we go on here. So the first generation is here. That's the first period, and that is for hydrogen and helium. But the second period also collect their modules like this, and they can grow and combine. But it's very complex to start drawing them, so you need to have some simplification, and that is simplification here. They are space packing also, of course, and the thing is that they first pack horizontally, like into differential surfaces. And you can see here, these, we can call them Daplo, but they do. And we see that there are three members here that are special, namely carbon, namely nitrogen and oxygen, because they are mid-symmetric. All the others are not mid-symmetric. We have the neon, for instance, the second of the noble gases, and that is filled with what we can call alpha blocks. So it's mature. So we must go on to next. But anyhow, I stay with the second period. And these are actually, if we the elements that we can see in next slide here, and then finally come to the results. These are layered in differential surfaces, and we know from differential equations that this can be very large, and in the term of atoms, we know that they can be 1,000 and 10,000 as wide as the elements themselves, which do form the knots of the Persian rug that is layered here. But then how become an atom, which is built by very many knots? Well, they do their trip here, and they come back to the corner, and then they go up to next slice and combine it. And then we have the ready atom when they comply with the physical situation, often when they are as high as wide. And then they are billions of times larger than the original elements. And we know that's the mystery of atoms. They are crystals. How can waves be crystals? And how can there be so many? Yes, because they must constitute of quanta. And the funny thing is that Lee himself called the things, he called them quantiteter, quantities. So the quantum mechanics is actually inherent in the original Lie groups, but they are physical. So that means that we have, if we also introduce the hydrogen, which is also mid-symmetric, we have a set here of blocks, you could say, but you can also operate with the surface just. And this is the set that actually build the whole of organic chemistry. And now I can be quite rapid. How long have I got? Yes.
10 minuter.
Ja, 10 minuter. Ja, vi tar 15. Well, so, and I hope that the history here, although as usual taking too much time, are sufficient to substantiate that we do have building blocks here. And they can have isomeric forms, and I just take carbon and nitrogen and oxygen, which all strive up to the and the colors here is that of the noble gases of the respective periods, and that's coming back. So now we have a puzzle set, and we see what we can do. First, we make self-aggregations of carbon, and this we can do in various ways. And we just build like this, and we see that that complies very well both in a hexagonal and a horizontal form with observed structures, like here fullerenes, for instance. And also, if we take a photo of a graphene surface, it really looks like this, and not like this, which is a ball and pin graphics of graphene, which actually consists only of empty space, really. So we can go on and see now the systematic kind of build here. And we have CH, for instance, CH2, CH3, CH4, and so on, and they are all like constituted by their blocks, which are called alpha blocks and beta blocks or whatever. But anyhow, you can make around of them. And we see now the comparison with the other kind of development, these valence things built on speculations in lack of data, which we can call ball and pin, and which he can call calotte, so-called space-filling models, and there are a lot of others. But we see it's not so easy to combine them. To make them fill space, for instance, is not easy, and to imagine that we have extremities and small blobs and so forth and so on is just not scientific, but it still makes up the whole iconography of present-day chemics. And we see that these are all layerable to space-filling surfaces or blocks. So we have to rush a bit, and I go on to next slide. Yeah, now we can take the carbohydrates, for instance, ethane, propan, butan, pentan, hexane, septan, octane, go on to plastics really. And we see that they are made up by their respective elements, and they can be dislodged. But I don't go to that now. I go to so there is a very high variability and permutations, you could say, because even the hexane and so forth and so on have a lot of isomers. And we start to find that you can do all kinds of like these isomers by these models. I just show you in the case of C5H10. You can take any C4H13 or something like that, and you can find the observed number. But I have to go on, and now I come to bigger molecules. And the carbohydrates, they also have oxygen and glucose. They also can form a lot of isomers, and they can also go into longitudinal structures, which in this case is cellulose, but also starch and so on. That is all glucose, you could say. But you have fructose also, and that is also C6H12 oxygen 4 in the oxygen 6 in the Berzelius notation. I take the liberty of make this, but they also have images in this case ball and stick, but this is which I say the real structure of them. But they are the same formula, but they are isomers and have various different properties. They have 6 CH and 6 OH. And we also have galactose, which is another variety with another diagram here, but where you have 3 hydrogen ions. And then we have fats, blood fats, cholesterol is very much C27, H46, and O. And that has actually a kind of portray in these notations, but it's still a bit hard to, but this is the actual structure. And we can see that this is also space filling sideways, but it isn't space filling longitudinally because it's still hooking up with tissue orientations and so forth and so on. But we go on to next one. And then we come to other fats, and this is a model of a phospholipids which contain choline and phosphate ion. I come back to the phosphate ion, which is very important, and glycerol, and then fatty acids. We can see how fatty acids looks. I made this contrast with blue, but they actually contain of this kind of repetition. So they are different from carbohydrates in that way. And this arm can be very long. I just have to stop here, but it can be very long and have various forms, of course, that all can layer to each other. And again, they tend to be self-layering, and we see that they fit nicely into the contours of themselves. And that is, I think, one absolute criterion of this. But of course, these forms membranes and so forth. These are the membrane forming, and we do have this also here. If you turn them on, and they can be very long, they form membranes. And we see here the chemical formula, and we see here the ball and pin. In this case, the calotte kind of diagram, and we can variate them. So, and we can make operations on the individual members, because if it is the real thing, it should of course be possible to make operations with them. And then I come to amino acids. I have reported them before, but amino acids, we have 20 odd elementary ones of them, essential. And what we must claim of amino acids is that they have a common width, so they can combine with each other. And I just see leucine here because it's important in the protein formation, and we can see here how a peptide bond is formed, for instance, and polypeptides and so on and so on. But the interesting thing is that they can form because they are like joined and form rings, alpha rings, and so forth. So they really can form the structures of proteins. Yeah. Mm-hmm. Now and arginine, that's another example of the same kind. And and then we have cytosine here. These are the nucleobases, because now we come to the DNA and RNA and so forth and so on. And this is how cytosine, which is one of these bases, is portrayed in space-filling calotte Basker model and in ball and stick and in network or waveframe, as it is also called. And I go on till uracil, which is also one base, which is the RNA typical one. I don't go through the others, but I come instantly to the essential component of both RNA and DNA and the phosphates and a lot of other structures, namely the phosphate ion. And the phosphate ion is namely one exception that we don't have hydrogen or because we have phosphate ion, but that is remodel, you can say, and give place. So we have phosphorus, and that is interesting because it has a neutron in it. But I just rush on, and I come to the phosphates then. Phosphates do contain a phosphate platform here, and we have the kind of ribose, the glucose moitié, and we have the base here, which is adenosine in this case, ATP. And I show monophosphates and diphosphates. And they can all be just built like this, but I won't have time for that now. And we have here, for instance, adenosine triphosphate. This is ATP, which is an enormously important molecule. And I show you in colors here that there are 3 phosphate groups, for instance. And this can be having various orientations in the glucose and the base. I show you the straight one, which will come back. But I also show what kind of flora there is of models of them presently. And even that the same calotte model could, for instance, have various. So it just don't go together really well. Here we then come to the phosphate deoxyribose. And that is when both the glucose, the sugar, and the base are angled. And that is quite interesting because then you can make them form, you can make them around, and then they will fuse. And they will fuse so that they will make one bandwidth per coordinate. I think this makes sense by itself. And we go on. Here we have, for instance, if we don't have angulated ribose, but straight instead, which you can reorient it. And then we get another combination, and that is making half a bandwidth per evolution. You can see you can make them approach here. Mm-hmm. Yes, they fit nicely within their so they really fill space also. And here showing how they look in comparison with the present diagram of them. So I'm quite soon ready, and I just show now the ribose, not a deoxyribose, but an extra oxygen. And that is the kind of material you have in RNA. And these are tending to be straight, like ribs, like rods. And the interesting thing that they have uracil instead of thymine. And that makes a gap in them because it doesn't really make the way to fuse. So therefore they tend to be single-stranded. But they are all possible to and I just show that single-stranded and also linear double-stranded, they exist above all in the microstructures. And if one looks at it in the kind of unique perspective, they form like this. And what they can also do, and that will be the final line of the presentation, one can also combine them to make like these hairpin structures. And this is still on the experimental plane, but it's quite possible to reproduce these kind of microRNAs and even mRNAs and transfer RNAs. But this is very dependent upon particularly good computer and because it's a lot of protein now coming in. How does protein help, and how is a protein actually composed? So it's a bit hectic and rapid, but it's all the time on the, so to say, working table, and these models can be manipulated and just like a puzzle set, composing things instead of portraying them. So thank you for that. And I hope you have a lot of questions now.
Thank you very much. Is there any questions for Professor Trell?
So those who are in this YouTube may type your question. I can convey this to Professor Trell, or those who are in Google Meet can unmute themselves.
Yes.
And directly can ask questions.
But
Ja, öppnar du igen så som du gjorde?
Ja, så. Men då öppnar...
We need to get our picture back. So, but you can just ask the questions if there is any, and we'll open up the view again. Ah, there we go. So now we're back. Let's see. Perfect. So.
And I'm on speaking terms, yes?
Yes.
Yes. Yes. Okay. Yes.
May I ask a question? Yeah, so thank you for your presentation. Could you please elaborate a little bit more on connection to Lie groups that you mentioned?
To Lie groups?
Lie groups, yes.
Yes, yes, Lie groups, group de Lie actually is the original, whereas Lie algebras now in current refer to the representation of the more electrodynamical models but Lie groups, Lie algebras were the original ones, and Lie algebras have been reinvented to just make these orbits and so forth, SU3 and SU4 and so on and so on. But the Lie groups, he himself realized that there were groups actually, but he didn't start to make continuous transformation group because that came as an effect of these original publications. And the only thing that I came to be aware of that we do not appreciate the full extent and width of Lie groups is that I can read Norwegian also. We Swedes, we understand Norwegian. And I struggled at that time as a cardiologist to see if one could make some kind of spherical group transformation of ECGs so that you can see where. And I read book after book after book after book on Lie groups and Lie algebras and found only a lot of horrible matrice operations and coordinate transformations. It can impossibly be coordinate transformations, I thought. And I saw these representation diagrams and so forth. So I went to Oslo and went to the library there. And there I found two exemplars of his thesis still lying in the archive. And I read them, and it took perhaps 5 or 10 years to understand, but in discussions with Mahim and later Ashok Adhikari, I understood that this was a real treasure. And but that was absolutely not then anything but of this. That was the original linear algebra, that was differential algebra, that connected with Newton and Leibniz and all. And the smallest unit, so to say, the smallest being, it was in that case theoretical work, but also immensely practical, because the line did the job as it should be in linear algebra. And then I found that he actually stated that Cartesius makes of the spatial coordinates an algebra in 3 dimensions. So he actually stated also that it was an algebra he made. And Lie groups came a couple of years, but they were already from the start also Lie groups. Because then he invented that this cannot be everything, even if it characterizes our word, that there is an absolute straight and then it's absolute round, and that happens things between them. He also realized that there are absolute infinity of various transformations that could be in between, so to say. And that started his group with the continuous groups, that he understood that there must be permutations, really, because you can have typically stupid groups, but you can have groups that, so that started his work with the continuous transformation groups. And that I think is fantastic, but it took him away from the basics, really. And the disposition and the disputation just lie there for 100 years, actually. There is a biography of Marius Sophus Lie in Norwegian language. I think it has been translated also, and that contains sceneries from the disputation. And no one understood a single word of it, they say. But they still got him good marks and so forth and so on. And he was, it can be said a lot about Lie, but...
Thank you.
Yes.
Thank you so much. If there is not any further questions, I have the pleasure of introducing the next speaker, which is Kirill Morozov. And he started his career in the Department of Radio Physics and Electronics at the University of St. Petersburg and in Russia in 1998, and earned his PhD in cryptography from the University of Aarhus in 2005. And he's currently working as an associate professor of University of North Texas in the USA. And the title is Using Untrusted and Unreliable Cloud Providers to Obtain Private Emails. That sounds very interesting. You're welcome, Kirill.
Thank you. So let me share my slides and I will start. Just a moment. I'll just need a second. A minute. Entire screen, and then I'll try. Do you see my slides?
Not yet. Yeah,
Not
it's coming.
Okay, now they're there. Okay, so if I nope, sorry. Let me do the full screen. Is it okay? Do you see my slides?
Yeah, in Bengali as well.
Okay, very well. So yeah, okay. Thank you for your introduction. I will start. This is I'm Kirill Morozov from University of North Texas, and this is a joint work with Nicolas Chiaputo and Ivo Desmet. So Nicolas was a bachelor student in our lab, and Professor Desmet is at the University of Texas at Dallas. So what I'd like to do, I'd like to quickly introduce my institution to those who may not know it and quickly talk about cybersecurity programs. And then I will go on to discuss email security, talk about related works. Then I will introduce the main ingredient of our work, which is secret sharing. Some of you probably know what it is, but I will not assume that. I will go to basics. And then a little bit more about the architecture and the software that we developed, and then conclusions and future works. So our university is over 100 years old, and it is considered Tier 1 research university in Carnegie's classification. So enrollment is over 45,000 students, and we're conveniently located in the north of Texas. So we have a bachelor and master program in cybersecurity. And our Center for Information and Cybersecurity also has a designation by NSA and DHS as a Center of Excellence. So without further ado, I will just talk about the topic of today's presentation. And by all means, please feel free to interrupt me. Unfortunately, the way I'm sharing the screen, I may not see you raising hands. So just please unmute and interrupt me, and I'll be happy to answer your questions. So the question is email security, and the major concerns that we have is, of course, we very commonly use email providers which give us service for free. However, in exchange, they can read our emails directly or indirectly. Google includes it in their policies. Others say that they don't look at our emails, but they have access to them anyway. So, and even if they don't, assuming that they don't, they also can be hacked, and also they can lose our data. So that will probably not happen with popular providers. However, smaller providers that could be used as well, if they lose their data, then our private information, our information is gone. Critical information could be gone. So yes, basically, I'd like to just argue that sensitive data leakage through unsecure email could be a major problem. So I'd like to use the report by Verizon. This is one of the major mobile and internet providers in the United States. So in 2023, they released a data breach investigation report. So I'll just bring your attention to those entries. So among the incidents, loss has about 15% share, and also about 25% of share of the causes of the information security issues would be email. So of course, we can also argue that maybe phishing is a big percentage of those incidents, but at the same time, since our emails go unprotected, we don't really know for sure what percentage of the incidents are attributed over the data leakage over emails. So for example, Professor Adhikari made an announcement about this conference over email. It was unprotected, so our adversaries now know where we meet, and intercept on our communication. So if we want to protect our email communication, the natural solution would be encryption, right? That's what we commonly use, but it would be only a partial solution. So, of course, if we look into very deep down in how cryptography is built, we'll realize that we need a key. So since we need a key, the key needs to be shared between the parties. And of course, we have standard internet security mechanisms that allow us to do it, like TLS. For example, when we connect to our online banking, we use this mechanism to protect our communication so that the attackers don't see our private information. However, there are several technical issues that we have there. For example, the so-called fail opening problem. If the email server does not support TLS, some of them do, then the email would still go unencrypted to prevent denial of service. And also in general, if we would like to use modern cryptography that is computational in nature, we will face several issues. For example, which algorithms or parameters to use, because algorithms become obsolete. We need to change them from time to time. Different standards exist in different jurisdictions. Also, development in quantum computation technology poses a risk to the modern internet security, and so on and so forth. So the question is, can we do better? Can we propose some solution that will help us to address some problems, or maybe add an extra layer of security on top what we currently have now? And it turns out to be possible as long as we are ready to assume that there are several communication channels between the legitimate parties. So we assume that there are several paths on which we could send information between ourselves, and then we also assume that the adversary cannot intercept on all of them at once. Okay, so maybe some, but not all. We don't know which. Before I'm explaining, before I go on and explain how to protect our communication in this scenario, I'd like to introduce the main ingredient, and it is the so-called secret sharing. So secret sharing is, sorry, I will just show everything. Secret sharing is a kind of a magic puzzle that will allow us or the data owner, who is called dealer, that's the kind of a technical term, to split the secret data into several participants. In the moment, I'll tell you who the participants are, but the point is, in secret sharing, we have the secret data or our sensitive data that we are going to split to some pieces, like pieces of a puzzle. So if enough pieces of the puzzle will be collected together, then efficient reconstruction will be possible. Okay, so that's natural requirement. However, the puzzle is going to be magical in the sense that individual pieces or some amount of the pieces that is considered forbidden set, not enough. For example, any two pieces of the puzzle will provide no information about the secret. You know, like in the regular like jigsaw puzzle, you can see, you can have a peek in the picture that is there. You may be able to guess what's there. In secret sharing, you have no idea what the picture is until you are able to collect the access set. And then reconstruction would be possible. So basically, the participants will just pool many enough shares together. They could just distribute them among each other or provide them to another party that will call a reconstructor and get the secret back. So finally, I want to show you some formulas, how to construct secret sharing scheme. There are several methods. Some of them, so I'm going to show you the one that uses abstract algebra, but there are also other methods that use combinatorics. So various mathematical methods could be applied, but this is the simplest to present. It was introduced by Adi Shamir in '79, and this is an example of the so-called threshold secret sharing. So the secret will be split into n pieces, and among them, any t pieces will be enough to reconstruct the whole secret. Okay, so for to share the secret, I will suppose that the secret is going to be an element of the finite field for some prime number, whatever I want. Sorry, for some prime number. And to share the secret, I will use a polynomial over the finite field. So polynomial will have random coefficients. And now, if I will, so the pieces that I'm going to give to the participants will be just evaluations of the polynomial at different numbers. For example, participant 1 gets evaluation at 1, evaluation at 2, and so on. In the general field, there will be some field elements, okay? They all have to be distinct, right? So the shares are the points on the polynomial, okay? Now it's quite easy. So we all know that using Lagrange interpolation, any subset of t+1 parties will be able to reconstruct the secret, okay? So what I told you before, actually, I was incorrect. Any t parties, any group of up to t parties will have no idea what the secret is, okay? That's what I write below. I stand corrected, my apologies. While the access set that I mentioned before, any t+1 parties will be able to reconstruct the secret. T+1 makes sense because using any t+1 points on the polynomial of degree up to t, I can use Lagrange interpolation to reconstruct the polynomial, get all the coefficients, and therefore the free coefficient, right? So I get the secret back. At the same time, I can also show that any subset of at most t parties has no information about S. So pretty much there are several ways of doing that, but it's due to the fact that the points on the polynomial, if the polynomial is randomly chosen, are going to be t-independent random variables. That's the easiest way to show it, but there are other ones, okay? So any coalition of up to t parties will have no information about the secret, and any t+1 parties will be able to reconstruct it. Okay, very well, so good. Now, how to apply it to email security. So look into this particular scenario. So there is a sender and there is the receiver. They all are, so each of them will be registered at n equal to 3 providers. Okay, so for example, this will be Google, Zoho, for example, and Baidu. Okay. So a little bit later, I'll tell you why this diversity, but yeah, 3 different email providers. And the adversary can control only one of them. So either one of them are just a bad guy who is after you, or they will be just hacked, and the adversary will be able to get all the information that is passing through a particular provider, okay? So now, details of my solution. What am I going to do? I'm going to use secret sharing, and any information that the sender, which will be the dealer in secret sharing, is going to send, the dealer will first use a secret share generation algorithm, split the secret into 1, 2, 3 pieces, and each pieces will travel via different providers, okay? And then the receiver will get those pieces together at their side. They will reconstruct it and get the secret back, okay? So remember that less than a threshold of provider, in this case, 1 provider, if n is equal to 3 and t is equal to 1, then every individual provider will have no information about the mails, right? They will all look like garbage to them, actually. But any 2 providers will be able to reconstruct them, okay? Our assumption will be that Google does not communicate with Baidu, Baidu doesn't communicate with Zoho, and so on, okay? So assuming that they do not collide, then you're going to have your privacy. So the idea itself actually is not new, and the idea behind the proposal that I just showed you is the so-called perfectly secure message transmission as introduced by Dolev, Dwork, Warts, and Jung in '93, and since then there was a large body of works about them. Interestingly, applying perfectly secure message transmission to the context of email security has not been done until 2009. So Oren and Wool actually proposed this idea, and they also had the implementation about that. So the point is, let's use secret sharing to protect emails. And only 2 out of 2 additive sharing was used. So long story short, I didn't present that. Basically, they can only handle the case of two providers. And also, they don't have data integrity. So something I'll mention to you in the moment, basically, if some of the providers act out or send some random stuff, then the legitimate party will also reconstruct a random stuff. So I'll talk about that in a moment. So an advantage of this work over ours is that they use the so-called linguistic encoding, meaning that the messages that are going to be sent between those two providers will be meaningful. Okay, so in our case, the message looks like garbage. They completely don't make sense. In this case, they look like some innocent messages. Okay, so they look like an actual text, right? It's just that it doesn't make any sense. So not it doesn't make any sense. It does make sense, but individually, the messages that each provider see has nothing to do with the actual message that they are going to send. Okay, so my point was that they do not look at data integrity. This is something that we would like to address. So the idea would be the following. Let's consider Lagrange interpolation. Okay, so suppose that one of the providers, like say there were 5 providers, and one of the providers just, instead of the actual share, sent some random stuff. Okay, so they could do that in principle. Why not? They could change their data arbitrarily. Now, during the Lagrange interpolation, then the receiver will obtain pretty much a random secret. Okay, so the malicious provider will not know what the secret is, but it will be something else, like not the secret that was sent originally. Okay, so share could be modified, and that's going to be a problem. So the solution that we are going to use, again, a kind of an old technology and an old idea of the so-called robust secret sharing, which was introduced by Rubin and Binor in '89. So basically what they showed, so the point was that as long as the number of parties that you have is going to be larger than twice the number of adversaries plus 1, then the secret can be reliably reconstructed from n shares in the presence of at most t malicious shareholders. That was the point. So the idea is to present some clever message authentication for every share. Okay, so in addition to sending a share, a piece of a puzzle, you will also add some kind of a checksum for that. So the question is how, so the technical question is how to construct that checksum. Still note that actually this scheme, as well as Shamir secret sharing, requires no pre-shared keys. So there are no keys that should be shared between sender and receiver. And we're going to have something that's called unconditional security. It means that, for example, quantum computers cannot break this scheme, actually, as long as our assumption remains correct that there are at most T adversaries and no more. So unconditional authentication, what do we do? Well, authentication is always about taking the message and getting the tag. The tag, which is called oath here, is going to be computed as a function. Tag will be computed as a function of the message. For authentication, we require a key. Okay, so the sender and receiver must have a key. So now I'm seemingly contradicting ourselves, because for authentication we need the key, but I said that there are no pre-shared keys. Actually, they will be pre-shared, but to different parties. Okay, so cleverly distributing authentication and keys will do the job. Okay, I'll show you how to do it, but yeah, I will not go too much into details about that. So the point is that the security that we have is that the adversary who may intercept message and the tag, and that's what the dishonest provider will be able to do. So they will control the message and the tag that they have for one provider. then they shouldn't be able to forge correct authentication tag for a different message. Okay, so if the message changes, then you cannot get the tag right. That's the point. So the construction, so the formal name is unconditional message authentication codes. That's what the cryptographers call it. And interestingly, what can be used as unconditional message authentication code is the construction that is very well known and kind of popular for different purposes in computer science are the so-called universal hash functions. I'm not going to go into details of that because I do not have time, but point is that there are many universal hash functions that has been introduced in the past, and many have simple design, but the problem is that they weren't quite efficient. So in our scheme, we want it to be sent over the internet, and we do not want the parties to spend too much time computing the tags and so on. So basically what we did, we just checked the known fast universal hash function designs, and we chose the PolyQ32 that was presented by Krovitz and Rogaway in 2000. So it's quite efficient, doesn't require a process of messages, and we can select the collision probability. So basically, this is the probability for the attacker to succeed, and AM is the number of field elements in the key. Okay, so the longer the key, the less chance for the attacker to succeed. So you could give me the probability that you want to have the chance for the attacker to succeed, and I could give you the key that matches that probability. That is how the function looks. It doesn't really matter. I mean, details, what I wanted to say, actually, the design is quite simple. So a few lines of code, and it's pretty efficient. So the next point, I have a little bit of extra time. So I just give you a very simple example of the Rabin-Benor scheme for the three-party case. So three parties will be three providers. And basically, the Rabin-Benor idea is to do the following. So, for example, let's look at the party one. So the party one has the share, so that's going to be Shamir share, the point on the polynomial, as I discussed before. And then there will be two tags and the keys. So the point is that the tags will be for the share S1, but the keys for those tags will be given to the other users, okay? So if this guy is a cheater, the guy will not have the keys for the tags. They will have to basically break the unconditional message authentication codes, okay? So, and this guy will have keys for two other parties. That's the point. Very hand-wavy, but yeah. Right. So implementation. Basically, yeah, you could do it. You could, of course, the idea is that you will have to use three providers, right? But in the end of the day, if I'm the receiver or I'm the sender, the messages will be handled on our side. So what we use the free and open source Mozilla Thunderbird email client, and then we implemented those secret sharing of the messages as the Mozilla Thunderbird add-on. And you could obtain it from the GitHub, and you could play with it if you are interested in. So add-on was written in JavaScript, and it also uses Mozilla's Web Crypto API to generate random values. So pretty much it will look like that. Regular window of the email client, but if you click here, then you will be able to secret share your message. So then you will be able to select the algorithm that you would like to use. So currently, you could do 2 out of 2 additive secret sharing if you have only 2 providers, or you could do TN threshold Shamir that I presented, or TN robust Rabin and Benor, okay? So basically, in the address book, you will have to designate the providers that you would like to use. for sending the message. And yes, when you click send, then the messages that will be sent to different providers will be automatically created. In every subject, we put the unique message identifier, and using this identifier, the messages will be reconstructed at the receiving side. Okay, so Alice will know that the messages, that the emails belong to the same message using that identifier. So, well, yeah, so this is not really a security proof, but what we get, we can get protection against two providers who are semi-honest. And also we can get protection against end providers as long as less than half of them are going to be malicious. So for example, if we have n is equal to 3 providers, then strictly less than half is going to be exactly 1, right? So if you have 5, you could handle 2 and so on, that's the point. So as an added benefit, Shamir secret sharing can be used to recover errors. So if some of the message are an error, then you could use Reed-Solomon decoding to recover errors in this case, or in case of Rabin Benor, actually you could recover errors from that many shares as is, because it also has authentication tags. I'm running a little bit out of time, so simulation results, yeah, the timing is kind of awful because we didn't optimize our implementation at all. So basically what it shows is that it kind of works in the reasonable time on a reasonable laptop, and you could get it faster if you get the optimizations. The limitations of our approach is that it's going to protect against malicious provider, but of course, if the attacker is going to monitor the message outgoing from the sender or message going to the receiver, then they will be in the same position as those guys, right? So this attacker will be able to just collect all the shares and get the message reconstructed, right? So what it means is that this is a good technique to enhance security of our scheme, right? So you will encrypt your emails, but as a second layer of security, kind of another line of defense, you may secret share it, like that's what we would recommend. You could also, yeah, so that's what I mentioned here. We could also apply different PSMT schemes. Some of them are not, some of them will have to be interactive. That's not really fun for email, but you could get some additional perks if you use them. And also, of course, optimization will be needed for our scheme just to make it more practical for large messages. If messages like 1 gigabyte, then our timing is not really good. So for the future work, one could also consider to extend this methodology for social networks. So basically, secret sharing the data across platforms, like you put your posts on different platform, and then no one will read them unless they will be able to pick them up from different platforms, right? There are some other questions that you could think about, like legal question, for example, if I publish something meaningless, is it a publication or not, and so on. So there are also kind of interesting things that could be considered here. Thank you for your attention, and questions, please.
So those who are in YouTube may type your question, or those who are in Google Meet may directly unmute yourself and ask questions. I will take care of the Google Meet one, sorry, YouTube link one. So Christina, please take care of others.
Yes. Thank you very much for this interesting, very interesting speech. And is there any questions for Cyril? Yeah, now we have in the chat. Is absolute security possible is the question.
So yes, assuming that the adversary is not able to get many enough shares. So under certain assumptions, yes. By absolute, I would specify perfect secrecy. Yes. Obtaining PowerPoint. Yes, I will share the slides with Dr. Adhikari, if that's all right, or should I just drop the PDF in the chat? I don't know what's better.
Yeah, you can drop it here, but the participants who are in YouTube may not be able to get that, so I can share with them. So you can send me email. Yeah, that would be nice.
Yeah, I'll share it with Dr. Adhikari, and then he'll share
those
it.
Those who want this share, the slides, kindly let me know over email. I have already shared my email ID. Okay, so any further question from Google Meet link, people?
Oh, thank you very much. So then I think it's time for our next.
Just a minute, few questions from here, this YouTube link.
Good.
Okay. So Shonia Sharma, she asked the question like, function should be invertible or not? So which function, I'm not sure, but.
So I think I saw another question about reconstruction. Maybe that's the same. Just a moment. How interpolation formula is used to reconstruct the secret. It is Lagrange interpolation, but you just perform it over the finite field. Similar story. Instead of division, use multiplicative inverse. It's that simple. Yeah, just so it will not over finite field. It will not look like a two-dimensional graph, but otherwise everything else works. Yeah. So actually, it works. Regarding the function that will be invertible, I'm not sure. Yeah, I need specifics. So for universal hash function, no, it won't be invertible. It's compression function. You can make it invertible, but there is no point of doing that. So yeah, universal hash function is normally not invertible because it's compression. Take long input to shorter output.
Okay, if this question, is the answer clear to you? Please type it there. Okay, and another question is, sir, can you explain the working of crypto API?
Okay. So just very shortly, you would when you implement secret sharing schemes, it is very important that you get the random values that you get are really unpredictable, because if basically they mask your secret, like if you mask your secret with predictable values, then you can have extra information about the secret just from shares. So shares are not really kind of perfectly hiding. That's the point. Therefore, crypto API allows you just to get random value as a kind of a function or API, and your operating system takes care of it. That's all, right? So you don't have to worry how random your value is. So you know very well that you cannot use, for example, rand function in C, because the output that it gives you is absolutely non-random, right? That's why you need to use crypto API, cryptographic API, to get randomness, or any other cryptographic functions. That's what I meant.
Okay, so another question is, sir, can you please mention a real-life example of hash function using in our smartphones?
This is a little bit, so I believe I believe you are confusing a bit here, not the hash function, encryption function. So depending on the smartphone that you use, different algorithms will be applied there. But all those algorithms, they have the so-called computational security. They use keys. They use short keys to encrypt long messages. And therefore, checking all possible keys allow you to break all modern encryption algorithms. With a secret sharing scheme, it is not possible. Why? A little longer explanation is needed. Yeah.
Okay, maybe in mobile, in end-to-end encryption, like SAR-256 or something, this has functions are being used. So in real life, so where you use end-to-end encryption, there you have hash.
Correct. Yes. So yeah. So SHA-256 you cannot use here for design of universal hash function because they are again computationally secure. So you need to use something else. That's why we use those specific hash function for authentication tags in Rabin-Benovsky.
Yeah. Okay. So I think that could be the last question. Since cyber security crimes are increasing, sir, how can we able to understand whether we are hacked or not? Is there any prevention method?
Yeah, so this is a very general question. Of course, it is difficult to know because after the incident occurs, you need to learn somehow that the problem occurred, right? So, it's difficult to find out, right? But backups is always a good idea. So just in case if something happens, like best protection against ransomware, regular backups on a correct schedule, right? So that if some issue occurs, you at least have your data. Yeah.
Okay. So thank you. I think no
Thank
questions
you.
from here.
Yeah, there were in the chats about can you achieve pure randomness, I think was the beginning of the question. Did you see that, Kirill?
Oh yeah. Am I still allowed to answer that? I'm sorry, I took enough
Please,
time
please.
already. Okay. So yeah, the question is it possible to achieve pure randomness because there is always a degree of connectedness? Yes, it is correct. So true random generators are expensive resource and it is difficult to get. So if you want a true randomness, then you probably need a special device for getting that. And I would strongly recommend that one if you want to use information threat security in practical setting. However, if you cannot have it, at the very least, you need to use cryptographic API available in your operating system to get something that is closest to the pure randomness.
Thank you so much. This was a very interesting topic. And now I think it's time for the next speaker. Very good. I can see that Carl Swops is currently here, and he's an independent research scientist and the president of Swops Inc. And the organization is engaged in color research. And he used to work in the White Sand Test Facility in New Mexico in the support of the Space Shuttle Engine Project and Space Launch System. So that sounds very interesting. And this talk today is the theory, basic color models 12.0, and basic music theory 7.0, and basic time hypothesis. Welcome, Carl.
Thank you. Can you hear me okay?
We hear you very well, thank you.
Thank you. Okay, is my presentation showing?
It's showing very well also. Thank you.
Okay, I'll get started. To start with, what I want to do is give some background, and I'm going to show some of my figures to try to get everybody on the same page in a matter of speaking, because what I'm working with is theoretical, and I'm definitely outside the box. And so I introduce numerous terms that I've invented as I've been doing my research, and to just start off with, um, I'm doing research with color, and that what I have identified was a particular pattern that's associated with color. And from that pattern, I've identified a harmonic that runs throughout the entire electromagnetic spectrum, and that I saw that if frequencies are frequencies, then I should be able to identify this pattern within mechanical vibration. So with color and working with the electromagnetic spectrum, that I was dealing with radiation. And when you go to mechanical vibrations, then you also get into music theory. So one of the things that came out from my research was that, yes, I can apply my color model to mechanical vibrations or to sound. And I also used this harmonic that I discovered. I call it Jacob's Ladder. And I was able to identify a correlation to basic music theory. And with that, I'm now attempting to apply those concepts to a basic time hypothesis. And that my research is found in the proceedings of MBIC. And if you go to my website, that you page down a little bit past what my current research is all about. And I have a listing of where you can find my previous papers, in the proceedings. So the primary focus of this paper is the basic conceptualization of time. Time will be approached as clock time T, and it's just a reference to, you look at the clock and, what time is it? And what my approach is that time is actually a temporal frequency. And a sustainable concept of time will provide a solution to Einstein's twin paradox and time dilation as a black hole is approached. And Einstein's twin paradox and time dilation as a black hole is approached are assumed to be opposite extremes of each other. And if you're not familiar with Einstein's twin paradox, this is just a thought experiment that he had done. And he said that you have two twins. One goes off in a spaceship and travels close to the speed of light and then returns to Earth. And when the twins compare their watches, the twin that remained on Earth was much older than the twin who went off in the spaceship. And my effort to get everybody on the same page, what I am going to do is jump through my paper, first of all, and show you some figures that I've worked out, and try to show you what I'm talking about. So the first page that I'm going to go to is page 5. And what I've am working on is that to keep from crashing into the work of Einstein, I've created my own space. I refer to it as spatial space, and I have temporal space and electromagnetic space. And in the research that I've done, that spatial space has a different orientation than that of temporal space and EM space. And the geometry that I'm working with is Metatron's cube. And with that, what I've had problems with is getting these two geometries to show in one figure. And with doing that, I can talk about something being in the same space. So in what I'm wanting to show or demonstrate is the geometry of the space, where you have spatial space, temporal space, in the fabric of space. And that if you look at this in terms of the Big Bang, that when the Big Bang happened, space and time came into existence. And what I was asking myself was that, okay, was this the same phenomena, and that space and time come into existence from that one event, or was there parallel events, or how is this all working? And then what connects space and time together to where you end up with the fabric of space that's constantly, or not constantly so much, but what we refer to. And where did electromagnetic space come into being? So I created my own kind of conceptualization of space, and that this, in a sense, would be positive space, and that I added a third tetrahedron, which was based on the Sierpinski triangle, to talk about the space that I'm working with. So adding the negative of that by flipping the tetrahedron and adding them together, that I'm back to the original Metatron's cube that I had started with. And so again, I'm proposing this as being a crystalline structure or a fractal, and that my talk is to focus on time, but what I'm also having to deal with is that what is the fabric of space? And we talk about things that are in space, and we talk about how space-time is curved due to the presence of mass, or the presence of something in it. But I was having some problems there. So with my modeling, what I'm wanting to propose is that spatial space is mass, and that the fabric of space is just that, it's a fabric. And that if it's crystalline, then with a crystal, when you apply a force, you get a charge. You apply a charge to a crystal, it vibrates. And the concept that I'm trying to develop is that you have mass that gets introduced, so you end up having like like an inclusion that's distorting the fabric of space. And that with the separate spaces that you have, that temporal space produces a temporal charge resulting in temporal vibrations, that you have EM space producing an EM charge resulting in EM vibrations. And I'm suspecting now that spatial space produces a charge and produces vibrations. And as a result, everything vibrates. And that that vibration is realized in the fabric of space. And so based on having a tetrahedron, you have to have 3 tetrahedrons in the base, 1 on top. And so each tetrahedron that you have in your structure has that form associated with it. Okay, now getting into the curved fabric of space, that this is 3-dimensional space, and it research talks about Euclidean space versus what's generally referred to as space-time geometry, which gets into 3 dimensions. What I was interested in was more 2-dimensional. I just wanted to track what time was doing. And the way it's been explained, I'm going to credit Einstein with this, but he had talked about vectors, and that there's a time vector, and that you use one of the dimensional vectors with the time vector to create your modeling. And that as the curvature of space increases, the time vector magnitude gets smaller. And as the curvature of the of space becomes flatter, the time vector becomes longer. And what I saw with that was that if I'm looking at the x-axis, I can talk about slope. And slope is typically associated with a line within a coordinate system, but I'm approaching slope in terms of the x-axis. So with the x-axis becoming shorter as curvature becomes greater, or if the curvature is less or space is flatter, that this would affect how time flows. And I'm trying to associate this with frequency. So from my note up here, talking about orbital mechanics, if this was Earth equals 1, that if you accelerate it, that it would push you to a higher level or into flatter space. Or if you decelerate it, you would actually drop closer in to the mass that you were orbiting, and you would speed up. And I'm applying that concept to time, that if you accelerate going closer to the speed of light, you go into flatter space, and that your wavelength would get longer. And if you decelerate, you'll speed up, and your wavelength, temporal wavelength, will become shorter. So as you approach a black hole, time runs faster. If you approach the speed of light, time runs slower. And time is in regards to frequency. It's not in regards to clock time T. And trying to work clock time T doesn't have the flexibility to do this. In fact, going back to Einstein's twin paradox example, that your watch will continue to work the way it does. And so even if your temporal vibration, and this is the vibration of the multi-dimensional fabric of space, if that slows down, your clock will still record time the way it always has. So a year is still a year, but that year would pass slower for you than it would if you were inside the Earth equals one orbit. And this is fighting me. I'm sorry. Okay, this is a kind of my depiction of just what I was explaining, and that this could be shown by slope, and that with this, that as the x-axis actually rotates over, that this is where the slope value is equated to a temporal wavelength, and from wavelength you can get frequency. So if this concept is not valid, yeah, the whole hypothesis falls apart. But Einstein talked about curvature. Curvature got into far more detail than I thought was needed for this. So I reduced the concept just basically to the concept of slope. And this is the other figure that I want to show you, where I talked about color and I talked about music theory, that this is a combination of the two systems. And I need to zoom out on this so you can get a better view of what's going on. That if I'm talking in regards to primary colors, that you have red, green, blue, cyan, magenta, and yellow. You have 12 reference points around here that what I'm trying to identify. And that with your orientation, 0 degrees is at top for spatial space. But in terms of harmonics and octaves, that primary red is at this location, and F is always to the left at the 11 o'clock position. And this is primary tone F, which is the vibration that everything seems to be in, that we can see through telescopes or whatever, with the light that comes from the sun. It's in primary tone F. And if everything else is in primary tone F that we can see, then it says that our universe that we can see is in primary tone F. And the actual octave begins at the 7 o'clock position and ends at the 7 o'clock position. And when you talk about a harmonic or an octave, it's like a spiral staircase. If you go clockwise, you're going up one level on the spiral staircase. And if you go counterclockwise, you go down one level on the spiral staircase. And that you also have the advantage of talking about primary tones, minor tones, sharps and flats, and that with the harmonics that I'm using what I call the 10x circular constants, which was another development that I made in working with this math, and that I'm using the proportions of the golden ratio to define my harmonics and the octaves. So color octaves and color harmonics are same in terms of things. This particular model is a model of the visible light spectrum. And the next item I wanted to show and try to explain. The other thing I want to explain here is that if I have red and cyan, that they're actually opposites of one another to where they are different things. And so when I talk about spatial space, temporal space, and EM space, and the number of dimensions that are associated with those, and a dimension is just a characteristic. That with this color model, I have 6 primary colors, and when you count the interfaces, I have 6 interfaces. So I have like 12 different characteristics with color. I have 12 primary tones that I could reference with that. And so with what I have, when I talk about temporal space, EM space, and electromagnetic space, that it gives me like 12 characteristics that I can talk about. And when I talk about the opposites as well, that gives me 24 characteristics. And when you talk about degrees of freedom compared to 3-dimensional space at 1 dimension at a time, that what this modeling does is gives you far more characteristics that you can talk about than just with normal space. And the other thing that I'm wanting to talk about is the twins traveling in a spaceship close to the speed of light. That twin that was traveling close to the speed of light was no longer sharing the same common moment with the twin that was on Earth. And this particular twin traveling close to the speed of light, due to time dilation, we wouldn't be able to see that twin, or he would, or she wouldn't be able to see us. And the question that I'm asking here is the twin traveling close to the speed of light an example of dark matter and or dark energy? And in the universe, has any mass ever been observed moving at a percentage or near the speed of light, or what's generally referred to as relativistic time? And we're back to the model that I had first presented to you. And if my modeling is valid, that this represents a particle as well as what you would see at the larger level or scale that was the actual universe. And that with that, I can now talk about a consolidated model that includes the orientation of spatial space and the orientation of EM space and of temporal space. And 28, 20. And I'm going to jump back to the top now. So what the thing that I'm trying to express here is that clock time t will be defined by Ohm's law and the velocity formula triangle, and that velocity flattens curved space. References to space, space-time, fabric of space, to me was very confusing because they could be used interchangeably. And the modeling that I'm doing kind of forces you to make the decision as to what are you talking about? Are you talking about mass? Are you talking about the fabric of space? And for my modeling, if the fabric of space is crystalline in nature, not that it is a crystal, but crystalline would just refer to where the atoms tend to line up. And with the modeling that I have for the fabric of space, that possibly we're actually seeing that, and it's being called the cosmic web that's out there. And Earth equals 1 ties in with this observation that I had made, that if the entire viewable universe is in primary tone F, the timing and clocking of basic music theory could be related to the enigmatic concept of the current moment or now. And with the paper that I'm working on that's following this up, I'm trying to answer that question. Is there something that we can use or see that will give us a value for Earth equals 1? And if that is possible, then when we talk about flat space being equal to 0, and that if the x-axis rotates to the vertical, that it's undefined, and between that 0 and that undefined mark, there's Earth equals 1. And it seems possible. I'm still researching this, but we may have the answer, and it was provided to us about 60 years ago when the cosmic I have it here. When the cosmic microwave background radiation was discovered. The problems that I had was when you look at like the Hubble constant, that the Hubble constant is a distance. It doesn't give you a frequency, but the cosmic microwave background does. And it's at about 160 gigahertz. But it also has a range that's associated with it. But most of the energy that we witness is at like 160 gigahertz. And even when they're trying to figure the Hubble constant as to how fast the universe is expanding, and this is how fast the different galaxies are moving away from each other, that one method uses the cosmic microwave background, and another method uses what's referred to as a standard candle. And the standard candle is looking at a type 1a supernova or some other object that the known brightness and characteristics of that item is known. And my question to me was that if you're looking at something that is in a gravity well, doesn't time dilation apply to that item? And when you look at the concept of something being red shifted or blue shifted, are we actually talking about the stretching of space, or are we talking about time dilation? And that not knowing, what space is doing is makes it much harder to come up with what's going on. And with the modeling that I was doing, I was comparing the Ohm's law triangle to the velocity formula triangle. And what I was wanting to look at was if I related potential. Normally with Ohm's law, this is E, but I'm using E here. So I'm just potential, current, resistance. And I matched up the velocity formula triangle information with Ohm's law. So this is time, this is a displacement, this is a velocity. And so time was seen as resistance, and working out different items that I was just, playing with to see, okay, what's time going to do? And if I look at it in terms of Ohm's law, does this make sense? And the rationale was that if I get away from thinking about time and thinking about it in another way, okay, does the idea of clock time T make sense? And clock time T is very, very limited. You can't use it to really describe time as time. And time as clock time T is timekeeping, and it doesn't really address what time is. And so that's what my research has been about. What is time versus, what you get on a clock. So I had done a comparison, and going back to my research with color, I know that I can come up with a balanced equation that explains how colors are combined. So if red is 1, green is 2, it's equal to blue. And from here, you can combine colors and come up with a value, a correct value for what it is. And when you combine red, green, and blue, which you're subtracting blue from the other side or both sides, you end up with 0, which gives you white light. And I applied the same concept to temporal space, EM space, and spatial space, and says that my 0 is representing the balanced system of multidimensional space, or what my modeling is all about, which says that with flat space, it's in balance, and when you introduce mass, it causes space to curve, and that's when you get the crystalline type responses from space. So when you have mass in space, mass isn't just mass. You have mass in the interaction of the fabric of space that's going on. And knowing where and how time fits in to the whole universe, it could give us a better idea of what's happening, why it's happening, what the value of Earth equals 1 is, what it is. And again, my big crazy ideas that's driving my research is teleportation and electromagnetic levitation. But in order to figure out teleportation, you have to figure out what space is and what space is doing, what time is. And that if you can get time to go to 0, then distance is 0. And I don't expect to figure out, what teleportation is, but it's what's driving my research. So I have definitions where I talk about slope and curvature, and I've shown you what's going on here. And the question that I have also is, what if the Big Bang happened at relativistic speed? So if it happened close to the speed of light.
Excuse me, Carl. I think we're running a little bit out of time. How long do you think you have left?
I've talked long enough, really, and that all I'm doing now is just summing up.
Very good. So continue. So with
okay.
the summing up. Thank you.
And I've been through all of this material, looking at definitions. I already explained orbital mechanics. And I have a research overview of just what I had talked about. And then I just have just open issues in regards to the research that I've done. And that's pretty much it.
Thank you so much, Carl. It's very interesting, color and space and time. Is there any questions for Carl, folks, from the audience? I guess if there's a question later on,
Sure.
they can contact you. And this will all be available, I guess, on YouTube, I think is correct.
Yes.
Yes, very good.
Professor Arnold is already amongst us. So
Very, very good. So I will introduce then Professor Barry C. Arnold, who is Professor Emeritus at the University of California in United States. And he started his career at McMaster University and continued to go to Stanford University, where he received his PhD in 1965. And he has earned prestigious awards as a fellow of the American Statistical Association and Institute of Mathematical Statistics. And he's an elected member of the International Statistical Institute. So it's my great pleasure to introduce the talk, which will be around the flexible bivariate Pareto models. You're welcome, Professor Arnold.
Okay.
yeah, can you see a box with an arrow at the bottom?
Yeah, I did that, but I can't find my window. It doesn't show up on there. Didn't show there. And when I click
I
Windows,
think it took a little time. It took a couple of seconds before.
okay. Yeah, I pressed the arrow to present, and up came, and then it said choose what you want to share, and it says, and there are three things, and I clicked on Window, and when I look down at the windows, it doesn't have. What is it? Well, let me move down. Maybe there's more. No, it doesn't have the window that I have open that has my PowerPoint presentation in it.
Can you maybe try again?
Let me just try something different here. Wait a second.
Yeah.
I'll come back. Meeting. Okay, now I got it.
Okay, great.
Share. Oh, now I got your face, but
yeah, it's
what happened to here it is.
Yeah.
But it has that gray on. How do I get that? Can you
now
see
we
it?
see it and we hear you perfectly. So very good. Thank
so
you.
even though my screen has it kind of grayish, it works. Okay.
It
I
works
guess I'll
fine.
have to read my stuff. Okay, so if that's the case, I can't read. I want a slideshow. And does it go? No, it's not. I need to get to the slideshow.
Yes, and it's and the bottom right, you can choose the slideshow.
But I can't. I have a problem. It says that to where it's. I have an infinity mirror on there. How do I get rid of that?
I'm not sure.
Okay, can you so you can see your screen?
I can see the screen, but I can't read. It has this gray. It has the what's known as infinity mirror, which makes it it's very faded, and I can't even see the top of it to where it says slideshow and begin slideshow, and it doesn't seem to work anyway.
Okay, maybe can you just minimize the meeting link? That might help you. The meeting link, can you just minimize that one?
Minimize the meeting link.
Meeting link, that means the browser. Can you just make browser minimize?
End presentation.
So yeah.
Can you see that?
Yeah, we can
No.
see this. Yeah, we can see your slide.
Can you see it? And
Yeah.
and this side too?
Yeah, we can see your slide.
Okay, there's a picture on the screen of a part of Calcutta that most people don't see.
Yeah, but that's
that
in the
right?
next slide. Yeah, that's in the next slide. Could you please go to the next slide? Then I can see.
Next slide is some Calcutta traffic.
Yeah.
Great. Okay. Well, let me go back. And here's my title, Flexible Pareto Models. First of all, I apologize. I logged in using the last link that you sent me, and it
Yes.
got me to the meeting, but I didn't realize that I wouldn't be able to speak until you introduced me and and you said I wasn't there. So then I had to go back and try again. I apologize to everybody for the delay. Okay, we're going to talk about Pareto distributions. And this is our hero, Wilfredo Pareto, a gentleman born in France, and he passed away in Switzerland. He was a very active economist and taught economic theory in Switzerland most of his career, because as a young man, he was involved in politics in Italy and effectively was kicked out of the country for being a troublemaker. So he had to spend most of his career in Switzerland. Uh, Early on, he came up with an idea of how to model income distributions. He had the theory that in most populations, the distribution of incomes was such that the proportion of people whose income exceeded X, that F bar of X is the 1 minus the distribution function, right, was a negative power of X. And not only that, he thought that this rule worked almost everywhere. Any populations, whether you measured income in time in a week, daily, annually, lifetime, they would all have a Pareto distribution. And he was a very persuasive speaker, and so it became very much accepted that in socioeconomic settings, Pareto tails would be expected. Notice that in this model of his, the parameter sigma, which is obviously a scale parameter over here, shows up again over here as effectively a location parameter. And in a sense, he has the two linked together, and that doesn't seem like a very good idea. This we're going to call the Pareto 1 distribution.
Manny, just 1 minute. So your slide is not again moving. So
the slides are not moving?
No.
Oh, well then you. Okay, well I'll have to escape, and I don't know what to do.
Yeah, now it comes. Yeah, so it's now univariate Pareto.
Yeah, but that's not my slide. That's just the. Can you see that? And if I go to the next one, can you see it?
Yeah. We can see now from the left side. You can move.
I'll have to move it on the left side. Okay. Well, as long as it works, okay. All right. So this is the model that Pareto came up with, right? And we told that it had the two things that are in there. There's something called the generalized Pareto model, which became very popular 40 years ago, and it was such that if it was offered as an extension of the Pareto distribution. If k, the parameter k was a real parameter, if k is equal to 0, or if you take the limit as k goes to 0, this becomes an exponential distribution. If k is negative, it's the Pareto distribution. And if k is positive, then this becomes effectively a scaled beta distribution. Now, in fact, so it's three models all pasted together. And your data will tell you probably if a bounded distribution like the beta is appropriate or a Pareto distribution. So I don't think that this is particularly interesting. But the reason why it's popular is if you do the computations for k negative, in other words, you work out distribution means and survival functions, whatever you do, and you look at your computations and you'll say, hey, I could let K be positive as well, and it works out too. So what you got was a free lunch. You worked out the Pareto distribution questions and solved them, and just by changing the value of the sign of K, you had results for the scaled beta distribution. But I won't continue with that one. Univariate Pareto distributions. What we did was we will separate the location and scale parameters in Pareto's model. We call that a Pareto 2 model. And then, and notice it still has the property of the distribution, or the tail of the distribution, dropping off as a negative power of x. And I forgot, you're not seeing it. Now you see the right thing. This was the generalized Pareto. Now, here's a similar distribution that has the same kind of tail behavior is a Pareto 3 model. We just moved the parameter in the scale parameter. Let's go back up here. This one, instead of the alpha outside, we move it inside the square bracket, and we get this model. And then with that, we could obviously consider a power model of that. So using both parameters, now we have a 4-parameter model, which ought to be flexible enough to fit almost anything. Surprisingly, it isn't, but it's a very flexible model and has been quite popular. But in terms of analyzing it, there is actually an even more general model, which is useful. It loses the intuition for the Pareto models because it doesn't sound like it's going to be a Pareto model, but it does include all of the Pareto 1, 2, 3, 4 models, and it means that you can do a lot of analysis for those models using this more general model. And it's built from independent gamma distributed components. And it's due to William Feller in his book, Probability Book. So most people don't even know about it. It's sort of buried in that book somewhere. And I call it the Feller-Pareto distribution. It's a very flexible model. It doesn't look like a Pareto model. Here it is at the bottom. X is equal to location and scale. Fine, that's easy to understand. But a ratio of 2 independent gamma variables with parameters gamma 1 and gamma 2. That is the Feller-Pareto model. And it includes all of the models we've seen so far. For example, the Pareto 4 model is just obtained by setting the last parameter in the Feller-Pareto model equal to 1. So that just says that it means the last parameter is, this is kind of tricky going back and forth here. The last parameter equal to 1 is gamma 2. So the numerator would be an exponential random variable, and the denominator a gamma variable to get the Pareto 4 model. And the other models are again obtained by simplifying. To get to the Pareto 1 model, the first 2 parameters here have to be the same. We remember we said that Pareto kind of confused the location and scale, but there they are. But the advantage now is that we can analyze, since the Feller-Pareto distribution is constructed with independent gamma distributed random variables, we can do a lot of analysis, a lot of computation, a lot of simulation for sure, in a very easy fashion that works for all of these models. There's an even more general model, which was introduced by Stopper and Zandalotti. Incidentally, the income distribution research historically has been done by Italians. It started out with Pareto, following up in a huge amount of work done by Gini, who you've probably heard of for Gini Inequality Index. And subsequently, there were sort of parallel developments of statistics in Italy and in the US and England. And the difference between the two, okay, is easily described. In the English-American system, if you wanted to talk about variability, you looked at the population, you looked at the mean of the population, you picked a random person and saw how far away from the mean he was. And that, well, they usually squared that and to get sort of a variance. If you were an Italian, you didn't do that in that population. You picked 2 randomly selected members of the population and saw how far apart they were. Okay, and that leads to sort of a Gini measure of inequality as opposed to the variance measure that was popular in the others. So there were whole developments of statistical analysis that were similar, but use this same basic or this differing just definition of what we mean by variability. Okay. Okay. In terms of inference for all those Pareto models, their component variables have gamma distributions, and so we can get moment-based estimates easily. And we also, the parameter mu, the location parameter, almost always will be estimated by taking the smallest observed value. In some cases, for example, in the case of the Pareto 1 model, that would be a maximum likelihood estimate. In fact, in most cases, it comes very close to that. The first Pareto 1 and 2 models are the easiest to deal with. Well, the title of my talk was involved bivariate models. But before I talk about bivariate models, I want to give you a little bit of history about multivariate distributions. The very first multivariate Pareto distribution was introduced by Kanti Mardia, a researcher famous for investigations in directional data and shape data, lots of things of that nature. But a long time ago, in 1960, he introduced the following, and this is the joint survival function. This notation, okay, this is not 1 minus the distribution function. This is the probability that x1 is bigger than little x1 and x2 is bigger than little x2, etc. And it has this is a simple form. And you can see that if it was one-dimensional, k was equal to 1, this would just be this would just be the univariate Pareto distribution. And so this is called the make sure we got that one. Okay, this is called the multivariate Pareto k-dimensional multivariate Pareto of the first type, and it has a vector of shape parameters sigma 1, sigma 2, and sigma k, and one inequality parameter alpha. Okay, well, that's a nice distribution, but once you see that, you can immediately figure out how to write down what would be a type 2, type 3, and type 4 models of this multivariate models of this case, where effectively we introduce a few more parameters parallel to the case in the univariate situation. And notice that in for example, the type 4 model, we have a vector of location parameters, a vector of scale parameters, a vector of shape parameters here, but one common value of alpha. That effectively gives us, it turns out that that distribution has some very nice properties. Let me just talk to you a little bit about the situation where you have a multivariate distribution. It's very unusual to have the marginal distributions of the same type as the conditional distributions. True for the multivariate normal, but generally it's not true. But in this case, it works nicely. That's why Mardia's distribution is very popular, although it has limited applicability. But the notation we use, we take a vector x and split it into 2 parts. X is k-dimensional. X dot is the first k1 coordinates. X double dot is the remaining k2 coordinates, where k1 plus k2 equals k. And if we have x having a multivariate Pareto, k-dimensional multivariate Pareto distribution of the 4th kind of the Mardia type, then it's easy to see that to get the marginals, you just have to, let's go back and look at this, to get marginals, you just have to set various u xi's equal to mu I, and so that those terms disappear, because if you want to get the distribution of the of all but the last variable, then you just take xk and set it equal to mu k, and what you now have is the probability that x1 is less than little x1, x2 less than or equal to little xk, and finally, no constraint on xk. That's exactly the marginal that you want. So the bottom line of that is that we can read out that the marginals are again of the same type, but with reduced vector parameters, of course, because they only have k1 dimensional parameters instead of k-dimensional. So mu dot is, with our notation, the first k1 coordinates of mu, sigma dot, first k1, etc. So that was nice. But there's even more surprises. If we look at the conditional distributions, if we look at for a fixed breakdown of x into the first few coordinates and the last coordinates, and we have it with a k-parameter multivariate Pareto distribution. The conditional distribution of x dot, given that x double dot takes on a particular value, little x double dot, so that's conditioning on, is again of the same type, but now of dimension k1, but it has mu, which is replaced by mu dot, the first k1. Gamma is the first k1 parameters of t, but we have a different sigma vector, which is a little more complicated. But the beauty of the thing is that the whole family of conditional density distributions is again of the Mardia family, and that's very unusual. And in some sense, it probably comes close to characterizing that distribution. Parallel case is multivariate normal distribution. We know that multivariate normal marginals are multivariate normal, and multivariate normal conditionals are again multivariate normal. So that's a very unusual other case, and I don't really know many others that behave so well. Okay, one little observation that turns out to be useful when we were trying to figure out the location parameter. If you take a sample from the Mardia distribution and look at the coordinate-wise minima, okay, it also has the same distribution with a modified shape parameter. The last parameter, instead of being alpha, becomes n alpha. So minima are in the same family. Okay. Well, to compute moments, etc., what we do is we use a representation of the Mardia distribution, not the one that he didn't give this representation, but it's available. We can write that X has a Mardia k-dimensional Pareto distribution if Xi is of this form, mu I plus sigma I, Wi divided by Z, where Z is an exponential random variable, which is I'm sorry, no, which we know the W's are exponential. I'm sorry. The Wi's are exponential and Z has a gamma distribution. Okay. More generally, we can consider a multivariate fellow Pareto distribution. Again, building it up using independent random variables. But now instead of having the Wi's being independent exponential random variables, we make them gamma random variables with shape parameter beta I. So that's a more general setup. Now, a much more general model, which is usually not considered, will instead, remember back here, remember that we had the Wi's had a subscript, but Z was the same for all of the I's, okay? Well, we can get a more general result from that by letting Wi, the W be different for each I, and the ZI's also. And that model is more flexible, and I don't think it has been used very much, but it certainly has an advantage of being well behaved. And of course, you can make that even more general because, okay, the basic component of the k-variate fellow Pareto distribution is a multivariate beta distribution vector of the form 1 over Z times W, whose marginals are beta distributions of the second kind. Let me remind you, beta distributions, the usual kind, okay, well, the second kind is a ratio of two independent gamma variables. The usual kind, type 1, is x over x plus y, where x and y are independent gamma variables. Okay, so people looked at bivariate extensions of the first kind beta distribution, and one of the first ones that was ever introduced in a context of analyzing educational data, was introduced by Libby and Novak in 1982 and rediscovered 20 years later by Jones and then by Olkin and Liu. And the most people refer to it by Ingram and Liu's names, but having seen the construction of the Olkin-Liu bivariate model, which is a bivariate model with beta 2 model, so it's going to be ratios of independent gamma variables. So The problem with the Jones-Olkin-Liu model is always had non-negative covariances. And we want more flexibility in our models with more covariances of either sign at least. And so we introduced a model which is built from 5 independent gamma distributed random variables, and it's of this type. And you can see that we start with 5 independent gamma variables with different shape parameters. And we define x1 to be u1 plus u3, u4. Okay, we have to explain what the roles of these things. Notice that u1 only appears in x1, u2 only appears here, u3 appears in 2 places, so that means these x1 and x2 are dependent. u5 and u3, 3, 4, and 5 are dependent. It make us have more dependence. Well, having seen that, we could look at a k-variate extension of that model using independent gamma variables. And it looks like this, and where ui's and vi's are independent gamma random variables, and w is a further independent gamma random variable. But seeing these models caused us to think about what is the most general kind. Okay. Okay, so these are just very general kinds of Fell-Pareto distributions that way. This is we're going to go back and look at the Olkin-Jones model because we want to figure out what is the most general model that is of the type that we have here. It's a situation where we have in the numerator gamma variables and the denominator gamma variables, but we have some dependence between the two of them. And what we thought about was some of the other models would have a numerator, a sum of independent gamma variables, and the denominator, a sum of independent random variables. And so we asked ourselves, what is the most general bivariate beta model, okay, that is built out of independent gamma random variables and has the following property, that the numerators are sums of independent gamma variables. The denominators are sums of independent gamma variables in both cases. And also, of course, the numerator and the denominator have to be independent. And here the numerator and numerator and denominator have to be independent. But now, what is the most general model of that? I say that it involves 8 U's. Let's look at their roles. U1 appears just in the numerator of V, U2 in the numerator of W, U4 in the denominator of W. So 4 of these random variables, U1, U2, U3, and U4 just appear in one place. U5 appears in both numerators, nowhere else. U7 appears in the numerator and the denominator, okay, nowhere else. So we have 4 variables that appear in just one place. We have 4 others that appear in just 2 places, and they're different, right? U6 is both denominators. U8 is denominator of V, numerator of W. And the question, well, could we have a U that sat could we have an additional U to go in here? Or could we have a U that appears in 3 different places? Well, if a U appears in 3 different places, it will destroy independence of numerator and denominator for at least one of the V and Ws. And if you try to throw in a new U, a different one, U9, if it appeared only in one place, it would just combine with one of these others to just change the shape parameter and still be an individual gamma variable. If the new random variable you had was going to be thrown into 2 places, like maybe we'd put it in both numerators, it'll combine with U5 and the model has not been enriched. So this is the most general model that you could come up with. Okay. Sorry, my phone doesn't know that I'm presenting. One ratio, okay. Now, this is a A fellow Pareto bivariate model would be of this type, but what we'd like to have is that the Z12, Z11, Z12, we would need to have the numerators and denominators independent, but we'd like to have some dependent structure between the two of them. And so that was true of the most general model. We'll go along to this situation. Here's our most general bivariate fellow Pareto model. And it's built using those UIs that were used to construct a beta 2 distribution. Remember that the clever thing about the fellow Pareto distribution was that it was just a location and scale parameter of a power of a beta 2 distribution. And so this is perfectly general, and the flexibility is enormous here. And of course, this has too many parameters, right? 8, 9, 10, 11, 12 parameters. But simplified models are obtained by just deleting some of the UIs. And so it's a very flexible family of models which you could use. Okay. Here's an example of the simplified model that has some dependence still, because remember that U8 appears in 2 places, okay? But the numerators U6, U7, and U8 are independent, so the numerator and denominator are independent here, and the same thing is true here. So so you have a lot of things you can play around with, and now, even after we impose, now to get a general bivariate Pareto 3 distribution, okay, it'll be of this form, but we have to have a situation where the numerators and the denominators both are exponential random variables. For the Pareto 3, yeah. And that we just put these 4 constraints on the deltas, but we still have 4 parameters to reflect dependence there. So we have still a very flexible model. For a Pareto 2 distribution, we just have to put in 2 constraints, and we have that. Now, I didn't even notice what time I started, but I'm sure you were very tired because we got going late. In complete generality, things get very complicated. Suppose you want to do a 3-dimensional extension of what we've done. The Arnold-Ing model, which for bivariate distributions had 8 values, so it was I lost where it was. Here, this is it. This was the most general bivariate beta 2 distribution with components which were sums of independent gamma variables. Okay, and so we would then say, well, we want to have a 3-dimensional bivariate, a trivariate beta 2 with gamma components of that same structure. And if we want to do that, okay, then it's going to be really more complicated. The 3-dimensional extension, instead of 8, we have 26 independent gamma components involved. It looks like this. I've been tempted to have a T-shirt made with this equation on it, and so when people see it, they think that I have some secret code that I'm walking around with. It would be especially fun to go through the customs area with this on your wearing this shirt. But anyway, look, you can see that you really do need 26. There are 1, 2, 3, 4, 5, 6 of these variables that just appear in one place. There are several of them that appear in 2 places. Some of them appear in 3 places. Can we have any appear in 4 places? I don't think so, because if we had them appearing in 4 places, then we would have some dependence built in. So that's now the question is, if you're still awake, and it's getting late for you, I'm sure. Okay, of course, the models include many popular models of special cases. You set lots of the lots of the delta j is equal to 0 to eliminate the number of but still keep some dependence in there. Now, the 4-dimensional model involves 80 components, okay? The 3-dimensional model involves 26 components. The 2-dimensional model involves 2 components. So we have 2, 8, 26, 80. And as part of your IQ test, you're supposed to answer what's the next one. Well, the k-dimensional one has the form 3 to the k plus 6k minus 1. The 6k are location and scale parameters, but it's 3 to the k minus 1. So that instead of 80, you're going to have 3 times that, which is 240 minus 1, 239. Okay. So remember, 9 minus 1 is 8. 27 minus 1 is 26. 81 minus 1 is 80. I'm sorry. And then 243 minus 1 is 242, etc. So you can finish it up. Now, very briefly, inference. If we have once again, the minimum is a good thing to use. To estimate the location parameters, you use sample minima, and corresponding information matrix is even available even for the fellow Pareto model, but I don't think it's particularly useful. And then there are a variety of estimations available for the Pareto 1 case, because in that case, by taking logarithms, we end up with a shifted exponential model, which there's all kinds of things that we can do with that one. So that's very easy. Moment-based estimates are usually available because of our construction involving independent gamma distributed components. And then the question is, can Tom Bayes help us? Well, of course he can, in principle. What people usually do in Pareto 4 case, independent and non-informative priors are used, but that's just like maximum likelihood. But if you like to convince your friend that you're a Bayesian, you could do that. And in the Pareto 2 case, in the Pareto 1 case, informative conjugate priors for the 2 parameters are available. Indeed, Lewin provides a minimal conjugate class. And another suggestion is you could consider conditionally conjugate priors, which give you even more flexibility and also have the advantage of being tailor-made for subsequent posterior Gibbs sampling to estimate the parameters in the posterior. Okay, multivariate inference is more parameters and more difficulty. And you're going to have to do things, implement things, or you're going to have to work numerically or using or perhaps with some simulation, and often the case you'll assume some homogeneity of the parameters, or that many of the parameters equal to 0. Of course, Tom Bayes could help here too, but again, the situation is effectively a problem where you most likely use non-informative priors, although there are some cases where you might get some prior information from marginal data. Okay, it could get worse. You might have data which is subject to hidden truncation. In other words, you want to sample the x's, but in fact, there are some covariables, and we only get to see an x if its corresponding covariable is less than some specified value. A situation like that would be if you look at income distributions, income tax reports, effectively, people who get below a certain income don't have to file. And so what you get effectively is not a sample from the full population, but a truncated population. And now the final concept here, make sure that effectively, is if we look at the bivariate beta distribution, okay, if I set V star is equal to 1 plus V and W is equal to W over 1 plus W, okay, then I get a bivariate beta distribution of the second kind. And now what we can do is put constraints to make sure that V star and VW star have uniform distributions, uniform 0-1 distributions. That's made by delta 1 plus delta 3 plus delta 5 plus delta 7 equals 1, etc., etc. Finally, delta 4 plus delta 6 plus delta 7 equals 1. And that still leaves us 4 parameters. So what we end up with here is a 4-parameter family of copulas. Now, the reason why I'm telling you about that is because there are very few multi-parameter families of copulas available. Most of the ones that people use are 1 parameter with only 1 parameter to describe dependence. And you think about how people use copulas, what they do is they model the marginals using marginal data, and they paste them together with a copula that's convenient to deal with. The problem is most of the families of copulas they use only have 1 or at most 2 dependence parameters, which limits the nature of bivariate distributions that they are going to be able to accommodate using the copula approach. And now that is a good place to stop. And I thank you for your attention. This is where my home campus. This is my hometown beach. And once more, I thank you for your attention.
Thank you so much, Professor Arnold. It looks like a lovely place where you live. Is there any questions for Professor Arnold?
Probably no one's still awake.
Absolutely. But the time difference, it would be interesting to know what's the time at your place, Professor Arnold?
It's 9:10 in the morning now.
So that's a good time. But in India, it's later on, I think.
It's 10:39 p.m. Yeah, 10:39.
Yes.
So,
yeah,
but
almost
still,
a little past 10:30.
Yeah. So still, people are roaming around in our YouTube channel. So today we had 1,400 views of our channel. It's a huge.
Okay, I apologize again for not using the right link to get in, and it was kind of funny. I was waiting, thinking that you were going to let me in, and then I heard you say, "Well, he's not here."
Sorry for that. I mean,
yes, and I was sitting here at my desk saying, "Yes, I am."
Okay.
Anyway, I hope that enough people heard some of it, and that if anybody wants a copy of my slides, I'll be very happy to send them to you. Just send me an email.
Yeah. Okay, sure. I will share your email, and your email ID is already there in the proceedings, and the proceedings of IMBIC is already on the website. So it's already released on
it's
the
very easy. It's just barry.arnold@ucr.edu. So it's my name at UCR. So,
okay.
But I'm sure, but you've got it written down in all kinds, in several places, so it's all right.
Okay. Okay, so I can see that Shagor Haldar, he wants your slide. So yeah, it would be nice. So you can, Shagor, one thing, you can directly email Professor Arnold, or maybe Professor Arnold may send his email to me so I can share at the end of the conference. Whatever is convenient to you, sir. Okay, then thank you very much. And it's our great pleasure to thanks to all the invited speakers, along with, of course, the session chair, Dr. Christina Trail. And that's the end of this technical session, as well as the end of the whole day. So tomorrow, again, we are going to meet at 5:45 p.m. for the technical session. But before that, paper reading sessions, 2 parallel paper reading sessions would be there. And that will start from 3 p.m. So with that, hope to see you tomorrow. Thank you.
Thank you very much.
Good evening and good morning and good night.
And okay, then bye-bye.